Hello everyone and welcome to the channel. I'm Emmanuel, I'm an airline pilot, and welcome to our tutorial for the iniBuilds Lockheed L1011 500 Tristar. Today we are going to go over the entire procedures from startup to shutdown, and we are going to do all of this while handling the flight engineers panel manually. If you do want to make it a little bit easier, you can always use the automatic flight engineer to handle the flight engineers panel for you. That way you can immediately skip the flight engineers procedures in this tutorial. Now we are going to fly the British Airways Tristar from Heathrow to Barcelona, which is going to be a quick 1 hour and 30-minute flight across Europe, and in that time we will be able to explore the entirety of the airplane. Now, let's go ahead and start with what is provided and what is not provided. So I am going by the iniBuilds manual for the Tristar, and that one is delivered together with the product. Respectively, you can simply Google for it and download it on the internet. The iniBuilds manual, however, only provides the so-called flows, which are the things that you do inside the cockpit. It does not provide you with a normal checklist. The checklist is used after the flow is carried out to ensure that any important item that could have an effect on the safety of flight has actually been executed by the pilot. Therefore, we will have to use a third-party normal checklist to operate the Tristar correctly, safely, and efficiently. For that, if you simply Google for L1011 500 checklist or just L1011 normal checklist, you will quickly find the website freechecklists.net. And on that one, they do have a lot of Tristar manuals available as well, including some original operating handbook from Lockheed Martin. And right at the very top, you will find the checklist by Holger Ludwig, which is this one over here. I do recommend to download that, as that is an appropriate normal checklist for use with the L1011. Alright, now we will be using this throughout the entirety of the flight as normal checklists, but as mentioned, we are carrying out the procedures in accordance with the iniBuilds manual. Alright, so that much about our basics. Let's go ahead and have a look into the flight that we are going to do today. So this is going to be our flight plan of the day. You can see we are departing from Heathrow, then heading southbound and pretty much in almost a straight line across France down to Barcelona, where we are going to start the approach. Now, we are not going to bother with all the weather and stuff for the time being. The only thing that's really important for us over here is the fuel quantity that we're meant to carry, which is basically 21,000 kilograms. So do remember that for a little bit later. Now, if you do care in a whole tutorial on how to read and check flight plans, then I do have that available on the channel, but I don't want to waste that half an hour in this tutorial now. Alright, so with all of that, we now know what we are going to do, so let's jump in and get started on our L1011. Now, the first thing that we are going to do when entering the flight deck is to go down into the electronic flight bag. Over here, make sure that you have entered all your SimBrief data in the menu, and just to go over what we need over here to be able to follow the procedures shown today. I am using the navigation option for the INS. I would recommend that you switch the INS drift off for the purpose of this tutorial, but I will be talking about it in flight, so I am gonna leave it on over here. But if you want it easy, turn it off, up to you. Now, I've turned the altimeter synchronization on so that we don't have to set the captain's and the first officer's altimeter separately over here. What we have to set is the captain's and the standby altimeter separately, because that is basically what you would be doing in the real world as well there. Okay, and apart from that, I am using metric units and the rest of the settings as set on the screen. If you do want to use realistic parking brake, by all means go for it. Then you do need to press the brake pedals before pulling the parking brake lever. I turn it off for the time being because it's a little bit easier to operate with my current joystick's dead zones. Okay, and INS alignment time is set to realistic. Now with all of those set, if you want it easy, you're going to go for the flight engine autocomplete. You're just going to tell them to autocomplete the pre-flight preparation flow. But we want to learn how to fly the aircraft properly and understand its systems, so we are going to do that stuff by ourselves. Now let's go down into the OFP. We are going to press reload over here just to be sure that we actually have the latest SimBrief flight plan available, and then we can go to the load sheet and hit SimBrief import. That is automatically going to set all the figures as required from SimBrief. If you do want to change them, then you can change your total fuel up here at the very top of the paper flight bag, and over here we just wanted 21 tons. So let's go ahead and hit load. Apart from that, our cargo and our passenger weights are automatically set. It's also automatically distributing that cargo. So for us, we got everything in the front hold today, nothing in the aft hold. And the nice thing is that it automatically distributes the fuel as well, so that we got a nice weight and balance for our takeoff. Now, the automatic distribution will sometimes require us to manage the fuel in flight, and we will be talking that when we are getting to the cruise or maybe even the climb portions of this tutorial. But for the time being, you can just leave everything on automatic. I do just recommend to slightly increase the fuel over the SimBrief fuel, because it gives you the bare minimum over here when you click SimBrief import. So that's what I've just done here, increasing that a bit. Now that's everything we need to do in the paper flight bag for now, but I would recommend one more thing, which is entirely optional. That is going to the ground menu and connecting the ground power unit. Now we don't need it, we could use the APU immediately, but in the vast majority of cases the ground power unit would be used in the real world, and therefore we are using it in the simulator as well. Okay, and that includes our initial preparations. Let's go ahead and go into the normal procedures now, and we're going to start with the flight engineer's preparation. So let's go ahead and get going. Alright, so the first step in setting the airplane up is to set up our standby power system. Now, the way we do this is to, first of all, do a bit of a safety inspection, so that circuit breakers are all in. We check that the APU and engine fire handles are in. We check that the continuous ignition is unlatched, and unlatched always means that a switch is outside. Take a close look here. If we push it in, it's called latched. If we have it out, it's called unlatched. That is the terms that Lockheed has been using for this airplane, so that is the terms that we will be using in this tutorial as well. So in, latched, out, unlatched. So the continuous ignition is unlatched. Then we have the essential and number 2 radio master switches, which are over here. Those have to be latched. Then we check the landing gear lever, which is down. We check the speed brake handle to be forward. We check the flap and slat handle to agree with the position on the indicator. So you can see the flaps are currently up, so we position the switch up as well. From here, we make sure that the elevator trim is fully forward and the other trims are zeroed as well. So all trims are in 0, the throttles are closed, the fuel and ignition switches are off. The transponder over here is on standby. You can see that on the side down here. It's in standby position, and the weather radar is off, which you can determine by all those switches at the top over here being unlatched. Okay, and from there we are going to move on to the flight engineers panel. Over here we check the ATMs, which are basically air-driven hydraulic pumps, are in the off position. We check that our AC hydraulic pumps, which are those two, are unlatched. Then we check the galley power switches to be unlatched. The fuel pump switches are all unlatched. And then finally the master jettison and dump switches down here are guarded, and below the guards they are unlatched. Alright, finally we move up to the passenger oxygen switch, which is again guarded and unlatched. Alright, and with that our safety inspection is complete, so let's now go ahead and set up the standby power system. We check the battery to be off. Then we got the standby power switch located at the very front over here. And that thing goes on. We check the on-arm light, illuminates, and then we go back to the flight engineers panel to check that the standby power flow bar is on. From there, the DC and AC essential bus fail lights should be out. So those are the ones at the top and, well, technically speaking, down here on the bottom. And then we check for the DC and AC standby bus fail lights to be on, which are supposed to be those. So those two seem inverted in the version that I have right now. Okay, from there we move over to the DC meter and we check that we got a voltage between 26 to 28. The AC meter is on the inverter, and we can see that that's also producing a voltage and a frequency. Alright, from here on we are going to turn on the battery. We notice the fail light going out. We notice the standby power on arm light going out, and now we can arm the standby power and guard that switch. And with that, we've checked the standby power system. That way we now know it does work, and we are now on the battery. Now, from here on, the iniBuilds manual directs us to set the lights up next. I would recommend to turn on the external power first. So external power on, we check the on light and to illuminate, and with that we now have power. Now, once power is established, we are going to go ahead and start setting up the lights. So for the flight engineer, we got the backlights for the instruments here, and then right beneath that, the backlighting for the text on the panel. Then we have the floodlights on the top over there, which light up the panel in general, and going beneath that, we would have the desk utility light, which is basically going to light up the flight engineer's panel down here. From there, let's move forward and set up the rest of the cockpit lights. So let's take a seat on the captain's seat over here. And we got a couple of light controls on the side, and I would recommend at this point that you turn on the instrument lights over here and the glare shield lights. Now, utility lights and floodlights can be turned on as well. The floodlight just illuminates the panel in general, and the glare shield light, if we turn that one on, which is on bright by default, just make sure that it is, illuminates the glare shield over here. Now we do have two more lights located down here in the bottom, which is the center console lights and the engine panel lights, which basically control the lighting of the letters and everything on the center console and the lighting on the engine panel. And then we move over to the first officer's side. Over here we also have the instrument lights that we have to turn on. Finally, we are moving up to the overhead panel, and we got a couple lights over here. First of all, you got the panel instrument light up here. That controls the backlighting of the front panel, including the lights. Then we got the light panel here, which includes the overhead lights and the panel lights, which again controls the brightness of the letters, and then the backlighting of things like your HF frequencies and stuff. Finally, you do have a center console floodlight over here, which can be useful in the darkness because it does illuminate the center console down here. Don't need that during the daylight though. And those are the lights that we have in the L1011 cockpit. So with that done, let's move back to the flight engineers panel and start with the fire tests. So before starting the APU, this is important if you are not using ground power as well. Before starting the APU, we need to ensure that the fire detection and extinguishing system is functional. We find those at the top of the flight engineers panel. Ensure that the mode selectors are set to cover both loops, and then we can test loop A. We can see the A light illuminates, and loop B. Loop B light illuminates, and this should also trigger the fire bell. This is currently bugged, but in a future version this is probably going to trigger the fire bell again. Press the bell cutout button to ensure that the bell actually cuts out. You don't want to end up in a situation in flight where a fire warning would be constantly sounding, right? So bell cutout switch should cut out that fire bell. Now, when that test is successful, aka when you hear the bell and when the cutout button works, then we can deselect those test buttons, and with that we have tested the engine and APU fire system. So if electrical power from the APU is required at this point, then we can turn on the APU now. The same also applies if you want air conditioning. So if it's cold outside, you want to heat up the cabin, or if it's warm and you want to cool down the cabin, then you can start the APU right now. The way to do this is to turn on the master power switch. And if you already have AC power available, then we have to turn on any of the tank 2 fuel pumps. So tank 2 is that one on the very right and that one on the very left. So just turn on a single one of them like this in order to be able to feed the APU. Now, with that done, we check that the bleed air shutoff valve is unlatched, so out, the mode is on min, and then we can go ahead and start that APU up by pressing the APU start button and holding it until the door in transit light illuminates. Then you can release the starter again, and now you can monitor that the APU start is progressing up here. Now the APU start is going to take a little while until it completes, like half a minute to a minute or something. And the don't load light down here indicates that you should not turn any electrical power on the APU just yet. Once that goes out, you can turn electrical power on. Now, the way we do this is to move over to the electrical panel, and then we got the generator field breaker and the generator breaker. We close that line, then we close that line, and now the APU is providing power to the aircraft. You can verify that up here, rotating that switch to APU, and we can see that frequency and the voltage is now indicating normal at about 400 Hertz and about 115 volts. Okay, with the APU start now complete, we can go ahead and apply air conditioning. So let's go up to the engine bleed control panel. Now this looks complex, but it really isn't. So what we want to do is down here we got the cabin temperature controls. That is where the air needs to go. Up here is the sources for the air. So we got the engines, number 1, 2, and 3. And down here we have the APU. So what we want to do in order for the APU to be able to provide air conditioning, first of all to turn that isolation valve on. Then, depending on the packs that we want to use, we got pack 1, pack 2, and pack 3, we may want to turn on the cross bleed valves. Then we want to turn on the respective pack flow controls, and at this point with the APU I would just use pack number 2. And now we need to ensure that that air from pack number 2 can actually get down to the cabin pressurization control or cabin temperature controls. So what we're going to do is we follow that flow line that goes to the side, goes down. Now we want to turn on the hot air mode, and we want to turn on the isolation valve, and we can do the same on the right hand side over here. And now we've basically enabled a constant flow from the APU down here, through this, down to the cabin temperature controls. And that way the APU is going to provide air as soon as the APU bleed air shutoff valve is opened. So watch that at the top. Currently the ducts are showing 0 pressure. Now I am going to open the APU air shutoff valve. You can see that the ducts are now pressurizing. And that way we can also hear that the air conditioning system is now running. So that's pretty much as easy as it is. It looks complex at first, but you can really see you only got to close the respective flow lines. And that's it. Alright, so at this point we have finished the initial startup and power up of the aircraft. So let's now go ahead and start initializing our IMS. And if you're wondering, there is sometimes a little pause in here because I need to write down the time so that I can give you chapters in this video. Alright, so now the initial setup is done. Let's go right to the captain's panel and start initializing the 3 INS systems on the aircraft. You should always start initializing them as early after the initial power-up as possible, so that you get the full alignment completed by the time that you're ready. So we're going to take the mode selectors, the MSUs for number 1, 2 and 3, and put them all on standby. While the mode selector are on standby, we are going to go down to the INS, and now we got to do 2 things. First of all, go to the position page and check that you're seeing 00000N 072. That number is important, as it tells us the mode in which the INS currently is. When that is checked, we move the selector all the way to the right into the test position and ensure that all of the light bulbs are working. And when that is done, rotate it back to the position selector so that we can initialize the position. Now we are going to do the same on all 3 units before we enter the actual position, just to verify that they are all operational. Like this and like this, because if anything was wrong at this point, we'd still have time to call for maintenance. Okay, so all of that is done. Next up, we need to know what is our actual position. Many airports might have a board with the coordinates of the stand located right in front of you. Unfortunately, not this one. So we are going to go down into the charts. We go to Charts, Heathrow, Airport. Then we just scroll down. There is always a chart provided that includes the coordinates of the stand. And that one is it. So, we are at stand 317 here in London Heathrow. So let's go ahead and find that stand on here. So 317, here it is. And those are our coordinates. So we need north 5128.2. So we go down to the INS, and now we press that button with the N on here, north. Now let's enter the coordinate, which is 5128.2. So with the north button pressed, the insert light illuminates. Now we go 5128.2. We check that this is correct, 5128.2, which it is. And then we're going to press the insert button. You see that this changes the right side of the display unit. Now over here we got our longitude. So we go up here again and we're at west 00027.8. You always need to enter the leading digits over here. So remember 27.8. So we go down here, press the west button, 00027.8. Cross-check that this is correct. And we can see 00027.8 is checked. And now we're going to press the insert button. And with that, we've told the INS our initial position. When you're 100% correct or sure that this entry is correct, move over to the other sides or to the other panels, ensure that you're on the position initialization page, and then copy that stuff in. So 5128 to north, insert west 00027.8. Insert. And we'll do the same on our third unit, position north, that's 5128.2. Insert west 00027.8. Insert. Alright, now that we've told the INSs their initial position, we can switch the mode selectors into the align position. So that's 1, 2, 3. And with that, the units start aligning. Now, when you move the mode selector into the DSR track, or desired track, and status switch, you will see a number starting to count down on the right hand side here. When that number reaches 02, your alignment process is complete and you can switch the mode selectors from align into nav. At that time, you will also see the green ready light illuminate, which indicates that the alignment cycle is complete. And that is everything we need to do for the time being. We will get back to filling in the flight plan later on, but for now, let's go ahead and get started on the rest of the flight engineer's panel preparation. Okay, so let's move over to the Flight Engineers panel and start doing a little bit of work. Now, the Flight Engineers panel follows a simple workflow. It looks complex at first, but once you're actually familiar with the layout of the panel, you will notice that it isn't actually all that different from your typical airliner. Now, the panel scan follows this flow. Start at the top left, or at the top right, move all the way to the top left, then we're moving all the way down on the side panel to the fuel controls. Then we're moving over to the right, to the middle panel, up, down, up, until we reach the slab monitor over here. And then we go over to the side, bleed controls, to the bottom, ECS monitor, to the top, cabin temperature controls. So you basically go around the panel like that. And that is the panel scan flow. Memorize that flow. You need to know that sequence of events, because when you do, it suddenly becomes a lot easier to not miss out on any of those buttons. So let's go ahead and get started. Top right, brake temperature. We select a certain wheel, press the test button. Observe the indicator go up by at least 100 degrees. When that's done, release the test button, unclick that, select the next one, test. And same thing, looks good. Unlatch, latch, test, looks good. Unlatch the button, latch the last one, test, looks good. Unlatch the button. Moving on, we got the wheel well fire test. That's the same thing as the other fire test. Loop A, loop B, and you should hear the engine fire, or you should hear the fire bell at this point as well. Again, small bug in the version I'm using to record this. Then we're moving on to the turbine cooling air. Test system A, test system B. We have the nacelle pylon overheat detection test up next. Test. Again, all of those loops are illuminating, looks good. We've already done the fire detection loop test when we started the APU. If you have not started the APU just yet, do that test now. So, A, B, and when the bell sounds, press the bell cutout button and observe the bell cutting out. Thereafter, release the test switches again. Moving on to the top left to the fire extinguisher test, we press the test button and observe all the lights coming on, and then we press and hold the short button and observe the lights going out. Release the short button, they come back on, release the test button, and that's the fire extinguisher test. Moving down to the hydraulic panel, we observe that all the hydraulic quantities are at least 3/4 full, which is also indicated by the green line up there. Moving further down, we make sure that all the switches are appropriately latched, the ATMs are off, the electric hydraulic pumps and the PTUs are off, but now we're going to test them. So switch on the AC driven hydraulic pumps, then also switch on the PTUs. Again, you can clearly observe what the system is doing by simply following the flow line. So AC driven pump on, goes down here, and you can see hydraulic pressure is increasing. It also goes up here into the power transfer unit, and with the PTU on, we can also observe the pressure in that system increasing, and the same goes for the two systems on the left hand side. That way, we verify that all of the electric, respectively backup hydraulic systems are working, and then we can close and turn those off again, and the pressure in the system is dropping again. Moving down to the electrical system, we are going to turn on one of the galley power buses. Now, note that we are only turning on one, not all of them, because we don't want to increase the load on the system too much. So, use your electricals with a bit of thought. On the ground, we don't need to put any of the ovens or anything on in the galleys, only the coffee makers, so a single bus is okay for that. Next up, we check that the low pressure light on the IDG disconnect is illuminated, but we do not otherwise touch those buttons. We check that the generator fields are closed for the power source that we want to use right now, which is the APU in this case, and tripped for any of the others. Moving further down then, we got the tie breakers, and those are all in, so that the AC tie bus is actually getting powered from up here. Again, it's quite simple. Down here is where your systems are connected, the same goes down here. So all we gotta observe is that the flow lines from a source, so APU generator or external power, are closed down to where the system uses its power. Alright, and that's everything you gotta check on the electrical panel. Moving down then to the fuel system. We're going to start with a fuel quantity test. That's located down here. We just observed that all the numbers read 99.9 and the indicators go up. Then we can release that quantity test again. Next, we are going to check the tanks 1A and 3A to see if there is any fuel located in here. Right now you can see they're at 0. If fuel was located in here, we would later have to switch the transfer pumps on to get that fuel out of the tanks 1A and 3A into the tank 1 and tank 3. But we can see right now they're empty, so we can switch those back off again to see our standard fuel loadout. Now, moving further down, we are going to test all the fuel pumps. So we're going to switch all of them on, observe the lines coming on, and ensure that the low pressure lights are going out. And we're also going to test the cross-feed valves by turning all of those on. Now we can see that the entire fuel system is working, so we are going to switch them back off again. But remember, if you are using the APU, you need to keep one of them on. If you're not using the APU, turn them all off, because we don't need the fuel pumps at this point. Going further down, we got the engine tank valves, which are guarded and latched, aka flow bars are visible. And once refueling is completed, we can turn the refuel power switch off down here. Now, next up, we are moving down to the right. The fuel jettison panel is guarded and all of the switches are unlatched. The fuel control amplifiers are guarded and unlatched. Then we got the fuel used panel, and if any fuel used is showing, you can reset that using the fuel used reset switch on the side over here. From there we move further up to the engine oil panel, and we're going to test the engine oil pressure. Then we are moving further up, checking the engine oil quantity to be sufficient for the use of the flight. Next we move to the engine status panel, and this one includes the engine vibration indicator. Now we gotta test that in all its different configurations. So we start with the mode selector on norm and pick up selection A selected. Press and hold the test switch, and the vibration needles are gonna go up to about 4 units. Release the test switch, rotate the selector low, press and hold the test switch, and observe them all going to 4 units. And we're going to do that for all of the different systems, like this. Then we change from pickup selection A to B, and repeat the test. And again, we want to see the vibration units go to 4 for each one of those tests. Like this, and when we're done, we can go back to pickup selection A, and that's it. Now from here, we are moving on to the next panel. The movie cutout switch, yes, that turns off the projectors so that passengers can no longer see movies in the cabin, is unlatched and guarded. The clock is set for the correct time. And then moving down to the APU controls, we basically just verify that the auto fire shutdown switch is armed and guarded. Moving further down, this panel is unfortunately not simulated, a little bit of a pity there. And then we get to the right hand side. Again, the flight recorder panel is also not simulated, unfortunately. Otherwise, you would have to set the correct month and day and the takeoff growth weight, the flight number, and the number of the leg of the day. So we're doing the first flight of the day, so we would select leg number 1 over here. Also pilot identification to have that in the flight recorder as well. And then press the push to set button down here so that it saves that data on the flight data recorder. Moving further up, the wastewater switches are all in their unlatched position. Then we got the cargo fire detection system. Select the detectors to both and press the test button. And listen to that, the fire bell is actually working on this. So we do hear the fire bell and we see those lights illuminate and the cargo fire compartment smoke light illuminate. Release the test button and that stuff goes out again. Next we are going to do the short test on the extinguisher, like that, and the tone cutout button should cancel that bell. Unfortunately, can't really test that right now because we have to click and hold in order to keep that switch down, but you would also check that the fire bell goes out when you release that button. Moving further up, the smoke detection system goes to both. Then we do the test here as well. And again, we do get the fire warning and the duct overheat lights illuminate. Moving further up, the humidity switch can be latched or unlatched, but I would recommend keeping it unlatched unless you're like parking in the desert, because you're not supposed to use it above 15,000 feet and it's very easy to forget. Moving further up, the passenger oxygen, we already checked that earlier, is guarded and unlatched. The warning panel shows us, for example, lights when the doors are open and that kind of stuff. So just verify that any of the warnings you see over here is actually expected and makes sense at this point. Then we're going up and we got the oral warning system test. We start with the selector on the aircraft overspeed position. Press and hold the test switch. You can hear the overspeed warning sound. Then we got the cabin pressure. Works. Unsafe landing gear. Works. Unsafe takeoff. And this will also illuminate the possible reasons for it. So, cargo doors not locked, and the elevator not in the correct position. Right, then we got the flaps, which we are going to check up here. And that also works. Then we'll also have the galley smoke test, which is at this point not simulated, as you can see. And then moving up, we got the slab monitor panel. We are going to switch that one on, but of course we're not going to get any indications yet because the flaps are currently not extended. We make sure that the switch on the right hand side is guarded and unlatched. So from here we are moving over to the left to the engine bleed control panel. So the engine high pressure switches are in. That is basically your engine bleed air. When those are on, you're getting bleed air from the engines. Then we got the engine isolation valve switches, which isolate the entire engine from the entire bleed air system. Those are important, for example, in case of an engine fire, so that regardless of whether the bleed air valve is open, you can isolate the entire engine from the entire system. Next up, we check for the APU isolation valve to be on. We'll need that later anyway. Then we got the cross bleeds, feeding bleed air from one side of the system into the other. So, for example, if you want to use engine number 1 to feed the pack number 3, you would turn that one on, cross bleed on, and now air could flow all the way into the right-hand side. So right now we're only using the APU. For that reason, we only have a single pack flow control switch on. You can run all three from the APU, as you can see right here, but you would have to turn that and that off for the engine start later on anyway. And since the APU is strong enough, or since a single pack is strong enough to control the temperature in the entire cabin, you don't have to use packs 1 and 3 at this point. Only if you're in a very warm location, like in Dubai or in Southern Europe in summer or in the Caribbean, then you may want to use all 3 packs to be able to control the air in the cabin. So for us, for now, a single pack is all we need. From there we're moving down, and the turbine bypass is set to automatic on all 3. The hot air valves are turned on, and the isolation valves down here that are allowing air from whatever source it comes from to flow down into the cabin are both turned on. Now the what are those called again? The temperature control valves, I believe, are all latched, so switch is in. This is what it looks like when you turn them off. Basically what that does is to isolate a single zone from the temperature. So those are all in, and the cabin temperature controllers are on the 12 o'clock position, which is approximately 24 degrees, which is what passengers in aircraft generally feel very happy with. Aircraft temperature control is a little different from what you would do in a room, where 21 degrees is ideal. In aircraft it's 24. Don't ask me why, but if you turn it down to 21, you will have everyone complaining. Alright, next we're going to test the area overheat system. Put it to system A, press the test button, and we are going to observe 7 lights on the engine bleed control panel. That's area overheat 1, 2, 3, 4, 5, 6, and 7. Then we move to the front and check the 2 wing anti-ice lights being on, and then we check on the main panel for the area duct overheat light to illuminate down here as well. When all of those are checked, release the test switch, go to system B, and we test that separately as well. Again, 1, 2, 3, 4, 5, 6, 7, 1, 2, and 1. Alright, and then we can release the test switch and switch the area overheat detection system to both loops. Now, ground controller can remain on at this time. This basically controls the ram air doors located at the bottom of the aircraft. Now, that would probably go into a little bit too much system depth. Just ensure it's set on auto. Now moving over to the right hand side to the ECS monitor panel. This is basically the environmental control system. We are going to monitor pack number 2 since that's the one we're operating. We check that the cargo heaters are selected as needed. Normally you would use cold so that the cargo compartment is not getting heated in flight. But if you got any cargo that needs heating, for example live animals, or if you are transporting fish where the panel needs to be cold, then you make sure that the heaters are selected accordingly. On the temperature selector, you can monitor the temperature in each of those zones. Note that this is in Fahrenheit. Welcome to a US built aircraft. And that way you can monitor the temperature in every single one of those zones, where flight stations, flight deck, forward, mid, aft cabin, self-explanatory, galley as well. And then you can also check the cabin or the temperature in the different parts of the air conditioning and the pack system. I would usually put it to the hot manifold, because that's really what's going into the cabin here. Okay, now on top of that we got the cabin pressurization controller. A couple of things for us to do. So interestingly enough, the ground check is recommended to do in the iniBuilds manual, but in the actual FCOM it is not listed as mandatory. For that reason we are going to skip this. But if you do want to do it, you put the mode selector into the ground check position, ensure that the flight altitude selector is selected below the current airfield elevation, and then you observe that the airflow valve should start moving. As you can see, not simulated right now. So just ensure that this is in the normal position. The cabin rate selector is on the dot, which means automatic. The standby rate selector is set to the middle. Then we go down here to the manual pack control valves, and we latch both switches to illuminate the manual lights. Now we are going to press and hold the selector in the closed position to verify that the packs are actually operating. Like this. We can see that they are. So knowing that the outflow valves work, we are going to switch the mode selector back to automatic, and we observe them open again. Next up we go off to the left hand side. Over here we gotta set two things. The first one is the expected cruising altitude, and for that we got the flight altitude on the left side, and looking into our flight plan we know that we are going to cruise in flight level 350. Here it is in our plan. So we are going to rotate this altitude selector until the left side, the flight side, shows us 35, which equals flight level 350. Pretty much like this. Now, on the right selector, we need to select our QNH. So today that's roughly 1013, and if you are in Europe, use the millibar setting, which is roughly the same as hectopascals. So 1013. If you're in the States, inches, self-explanatory, same unit. Well, and that includes, or that concludes, setting up the flight engineers panel. And as you can see, it's not all that difficult, is it? So you just really gotta get used to executing the correct flow and memorizing which sequence of events you got to carry out. So from the top to the side to the bottom, then you go through here, back to the top, over here, and like this. And when you do it in this sequence, it's absolutely logical, and it actually becomes very hard to miss doing something, because you now got a fixed logic that you are following when you are operating the flight engineers panel. So with that, we have finished the flight engineer setup. So let's move on to the setup on the main panel. For that, let's go back into the captain's seat. So, starting at the very top again, we are following a panel scan sequence over here. And that panel scan sequence starts on the top over here, goes down, up, down, and then on the lights panel from the left to the right. So that once again you have a set sequence of events and a set scan technique on the entire panel. So let's go ahead and get started. We observe the INS to still be aligning. Basically, we don't want the fault line on. Then we go down to the compass. And over here, we ensure that the compass is set to magnetic and not to the directional gyro. So this is magnetic, and the button is on the 12 o'clock position. We got the HF radio, which is currently not simulated. Then we're moving down to the light test. Over here, we can once again press the light test button and observe that all those light bulbs are working. When that's done, release the switch again. The master radio switches are latched, the wiper is off. Now the cabin interphone switches are all reset. You can use the press to reset button over there if required, but by default, unless someone is actually calling you, shouldn't really need that. Now the engine anti-ice switches are all three unlatched. The wing anti-ice switches are all unlatched. And then getting up to the windshield heat panel, we should, over here, observe that the cabin and first officer switches are latched, like that. And this should illuminate the idle light. Currently not simulated, unfortunately. Then the side window switches are also all latched. And the fault lights should be out. Then we can use the test button, and this should flash the fault lights. Again, not simulated at this time. After the test, release the button again, and that's it. Now moving up to the air data sensor heat panel. Over here we observe the off lights, and all switches are currently unlatched. Moving on to the main panel then. Center console floodlight as needed. The Mach field switches are latched. The radar limiter switch is latched. Then we are going to test the flight recorder. Press and hold the test button, and you should observe the needle over here go to the right. Now, currently not simulated, so no needle there. Let's release the switch again, test completed. Engine start panel, select the engine start selector as needed. So, what's typically done is first flight of the day system A, then you switch to system B, and that way you just alternate around. Now the ground start release switch is unlatched, continuous ignition unlatched, the ground starter switches are all unlatched, and the windmill air starter switches are unlatched. Instrument standby lights set to bright. You can use the dim position at night if you want to. Passenger address, this is basically monitoring the PA system, the volume, so we can keep that off. Then going to the PFCS panel, all the switches are latched. Going on to the FCES panel, we want to observe the following. Basically, switches down here are all latched. And then we need to carry out the stall warning test. Now, this is, once again, currently not simulated. But the way you would do this is you press the test button, then you get the System 2 test, then you unlatch the System 2 switch, press the test button again, that tests System 1, thereafter latch both switches. Okay, now from here we are once again moving on to the side panel. Again, INS, we don't want to see the battery light. The compass is on magnetic and the switch is on the 12 o'clock position. Moving down, again, no battery light. AnySkid. So over here we also need to test the we also need to do the AnySkid test. So for that, we move down to the brake selector switch system and observe that that's set to system B. Now we release the parking brake and verify that the chocks are in position. So parking brake is released. Now we can see that the AnySkid system is coming on when the switch is latched. When that's done, we press the normal test switch, and this should illuminate all the lights. Again, right now, not simulated. Now release that switch, and then we press the Alt button, and again that should illuminate all the lights. Release the switch, and observe that when we turn the anti-skid switch off, or when we unlatch the switch, the off light is coming on. And with that, we are done with the test, and we can set our park and brake again. So moving back down here, we are moving further down to the auto brake panel, which is selected off, the wipers selected off, and that leads us down to the lights panel. Position lights are coming on, and all the other lights are off, except for the logo light, which you can turn on when it is night. Emergency lighting, armed and guarded. Magnetic compass brightness as needed. Fasten seatbelt switch on as soon as refueling is completed. No smoking switch on at any time. Eye locator light switch, which is basically down here as needed. I'd normally keep that one off. Thunderstorm lights, that basically turns on all the lights. That's the reason why it's a guarded switch, so just keep it guarded and unlatched all the time. Alright, and with that we're done with the overhead panel. So we're now moving down to the main panel. We're starting left to right, going over the entire panel. Note that I'm not going to do the glare shield just yet, because we will do that later on when we start the setup for our departure. So starting on the left, the clock is correct. Then we got the instrument comparator test, where we're going to press the switch on the top left. You can see all the flags and also the attitude flag on the ADI. And then we're also going to do the same on the right side and observe the flags again. Moving on to the AFCS warning switch. Again, test the left side, observe the lights, test the right side, observe the lights. Now this is our FMA, and this also has test switches that you can see down here. So press the left test switch, observe all the modes, press the right test switch, observe all the modes. Okay, moving further on to our panel, we are going to set the QNH as needed. Now we'll do that in a few moments when we actually check for our ATIS, or we just get it from a flight plan right now. QNH is 1011, so let's just set that. Alright, then we got our marker beacon lights, which we can test by pressing them, and they're all looking good. Moving on to the right side, max indicator reset. And what this does is you have some needles over here which show you the maximum value of a setting during the flight, so that when you exceed anything, those max indicators would just stay there, and that way you can see later on that you had an engine exceedance in the flight. Of course, prior to the flight, we do want to reset that thing. Then we got the standby altimeter down here, where the QNH is set. We can reset the master warning panel down here. Now this, as you can see, turns off any of the warning light, telling us up here that there is a warning somewhere on the flight engineer's panel in the back. Now, you can do this in the pre-flight, but a lot of warning lights are still going to come on during the rest of the pre-flight sequence, so some warning lights will be coming back on, so kind of up to you if you want to do that. Moving further to the side, landing gear lever is down and the 3 green lights illuminate. The brake pressure is up here above the amber range. And then we're moving over to the first officer's side, where we are once again testing the AFCS modes, left and right, the AFCS warning, left and right, and the instrument comparator, left and right. We ensure that the QNH is set. We can test the 3 marker beacons, and the instrument source selector switches are all blank, so unlatched. If you do press them in, that's what it looks like. Alright. With that, we are done on the main instrument panel, so now we're moving down to the pedestal. We got the pitch disconnect and the roll disconnect switches, which are in their pushed in positions. Then we move right down to the pedestal. Now over here, frequencies for the radios set as needed. The audio control panel selects where we transmit on the top, and then what we listen to at the bottom. We want to transmit VHF 1, and we also want to listen to that and turn the volume up. The same goes for VHF 2 and for the interphone. Now, if a marker is needed for your flight, you could also turn that on right now. If you plan to use the HF radios during the flight, and after refueling is complete, you could select the HF antenna, turn that on, press the push to talk once, and then you should hear a beep while the antenna tunes to the frequency. So that's only if you are planning to use the HF radios, which would be expected when crossing any oceans. or anything where you go into an oceanic control, or when you're flying across Africa. COM3 is set, ADF as needed, but we can already switch that on. I'm not going to set any of those frequencies yet, because we will do that later when we set up our SID. Then getting into the middle of the pedestal, we got the transponder, which is set as standby, ADC system 1 and altitude system 1 when the captain is pilot flying, and system 2 when the first officer is pilot flying, and the squawk as needed. Moving down to the weather radar, the antenna is set to about 5 degrees above, which is where it should be for takeoff, and no mode is currently selected. The gain is calibrated. So the aileron and the rudder trims are both at 0, and then on the right hand side we set the frequencies as needed. We set the audio control panel for the first officer, and we ensure that the cell call systems are as needed for the flight. So basically we'd typically be using HF cell calls, not VHF cell calls, and that's set. Now the right ADF goes on, and we'll do the frequencies later on. Now, when all of that is done, we move to the side, and down here we got the oxygen mask, which we can also test, and the way we're going to do this is to use the test mask switch, test both the 100% oxygen and the normal switch, and the oxygen supply, which is also going to give you the flow meter, and that's it. Alright, and that's the test completed. So, with that, we have now done the complete pre-flight procedure for our Tristar, and from this point we are gonna go on and start our setup for the navigation systems. So let's go ahead and get started with that. The first thing we need to do is to verify the runway in use, so get the ATIS, and then to verify which departure we're expecting. So at this point you could probably also already get your IFR clearance if you're unsure which SID to expect. If you know which departure to expect, no need to do that. Okay, then let's go ahead. Before inserting anything into the INS, we want to verify the standard instrument departure so that we know which waypoint the first waypoint to insert is. So on the OFP, this is the standard Lido format, by the way, using that one because it includes all the waypoints down here. So let's quickly understand what this flight plan tells us. We got the waypoint. Behind the waypoint, we got the information on how to get to the next waypoint. So you got your waypoint up here, and then everything over there is how to get to the next waypoint. Now you can see we got all the waypoints for the standard instrument departure on here. Question is, do we need all that? Now, in order to figure that out, we're going to have a look at our departure chart. So we're filed with a MAXID 1 Foxtrot departure over here. Let's go to Charts, Departure, and have a look at the MAXID 1 Foxtrot. Here it is. So let's have a look at what we can fly conventionally and what we need to fly with the INS. And looking over here, we are departing Heathrow, runway 27 left. So we go straight ahead, intercept radial 239 outbound from London VOR until 5.5 DME. We can definitely fly that conventional. Then we do a left-hand turn, intercept the QDR 160 outbound from Burnham. Now that one can also be flown conventional because we have that NDB. And we basically fly this to intercept radial 010, so that means track 190 degrees, inbound to Midhurst VOR, and we do that at 12 DME London. So you can see we can fly the entire SID all the way to MAXID conventionally without any need for the INS. Now just to get you in the loop over here, if you are flying a SID that is labeled as an RNOF departure, that means you will probably need the INS. However, the INS is not accurate enough to be allowed to be used for an RNOF SID. So if you have an RNOF SID, even if you know the coordinates of all the waypoints, you must not fly it using the INS. unless you want to simplify things for flight simulator usage, since nowadays many airports only have ANAF SIDs. But don't do that on VATSIM. If you're flying on VATSIM, just tell the controller that you're unable for the SID and you require radar vectors. Alright, in any case, we have determined that we can fly the SID conventionally, so let's talk about a bit of a nav setup. We said that first of all we need to fly the radial 239 outbound from London VOR. So let's go up here and tune London 113.6 and make sure that the DME is also turned on. At this point you could also do the DME test, where you put the switch into the test position and then you should see the off flags come on the DDRMI down there. Unfortunately that's not simulated right now, so just make sure that the switch is in the norm position, otherwise you can see, turning that off, we don't see the actual DME, so be sure that this is a norm. And the London VOR is now tuned, and we want to fly the radial 239 outbound, so we are going to select on course 1, 239. Like that. Okay, we're going to fly that to 5.5 DME, which we are going to see up here, and in the real world also up here, but unfortunately in the iniBuilds this is currently only showing INS information, regardless of the radio INS switch status. So when this is an INS, you should see INS information down here. When this is on radio, you should see radio information, so the DME up here as well. That's currently a bug. If they fix that later, by all means use the DME up here because it's easier to read. Otherwise, we gotta use the DME down here at the moment. Okay, so radio 239 until 5.5 DME London. Then we make a left-hand turn to intercept the QDR 160 outbound from Burnham, and that's on frequency 421. So let's go ahead and tune Burnham 421, and since we only need that one NDB for this flight, I'm also going to tune that on the second ADF so that we have a backup in case any one of our onboard systems does fail. So 421, 421. Okay, so now we're going to fly that until 12 DME London, so we still need this, but we are thereafter going to intercept the radial 010 inbound to Midhurst. Remember, radial is always opposite of the course, that's why radial 010, Midhurst has to be somewhere down here. Radial 010 is up here, but it's going to be course 190. So what I'm going to do here is to select a course of 190 on course 2, and now comes a little personal technique. Once we're doing that left turn over here, we no longer need the London VOR on our side to navigate. But we still need the DME. The next VOR we need to navigate the aircraft is going to be Midhurst down here, 114.0. So what I want to do for this departure, once we pass 5.5 DME London, we're going to turn left on a 160 QDR outbound from Burnham, and then I will switch the VORs to get Midhurst active on number 1, so that we can simply intercept that radial inbound. That means, in order to determine the turning point at 12 DME, we need London VOR on VOR 2 as well. So 113.6 into nav 2. It would be easy to be tempted to turn Midhurst down here, but since the Tristar does not have a standby frequency, but only active frequencies, the way I'm doing this is to use VOR 1 to fly this to the turn, then tune Midhurst on VOR 1, and therefore, to determine those altitude constraints here, we still need London. Therefore, I'm also tuning that on VOR 2. And that's the entire technique that I'm using to navigate this SID. So 190 is set as a reminder only on course 2, and will have to be set in the course 1 later on for navigation. Alright, and that's how I plan to fly this SID. Now we also need the runway heading for the initial takeoff, so let's just quickly go down, and I see I haven't pinned the airport charts yet. Let's do that real quick. Airport and taxi. Right, let's get that airport chart active. Here you go. Runway heading, should always set that. 269. Let's put that into the heading selector. Like this. And finally, let's open up that SID again. Initial climb is going to be 6,000. So let's select 6000 on the altitude selector. And note that before we get our IFR clearance, just as a quick reminder there that we're not cleared to climb to this altitude yet, before we get the IFR clearance, I would add 100 feet down there, just as a reminder. Now, you don't need to do that, but I would consider it good practice to do that. Since we are flying today's tutorial without ATC, we are going to select 6000. Next up is the speed. So this is only for the auto throttle. But this also currently controls the fast-slow selector up here. I do believe that to be a bug. I do believe this should be controlled via this speed bug over here. Currently, in the iniBuilds, this is bound to this. Therefore, I'm going to use this to set our initial speed limit. And since we do not have any constraint for the speed on this SID, we can simply select 250 knots. If we had any speed constraint, consider setting that. Alright, and with that, our entire guidance system is set up. Let's turn on the flight directors. Let's press the toga knob up here in order to actually get flight director guidance for our takeoff, and you can see toga is now the active mode. Alright, and finally ensure that if you want to use the VOR2, you also got to switch, or the DME2, you also got to switch that on that side. Okay. And with that, we have finished the setup for our SID. So now that we know from which waypoint onwards, aka max it, we need to use the INS to navigate. Now we can go ahead and start entering our flight plan into the INS. So in order to do that, we got a couple more things that we need to do. So let's go ahead and start entering our flight plan into the INS. First of all, get that flight plan. So I'm using the SimBrief app over here, but what I would really recommend is that you pull this PDF from SimBrief onto a device where you can enter something into the flight plan. So I am using the app Goodreader, and no, I'm not sponsored to say this, I'm using that thing for over 10 years now. I'm using the app Goodreader to open that flight plan PDF so that I can actually draw inside the flight plan. If you're using other devices, totally fine, but get something. You can even print it if you want to be as historically accurate as possible. Just something to allow you to draw something into that flight plan. Now, what we're going to do is we have determined earlier that we can fly all the way to max it on conventional navigation. So for our flight plan in the INS, since we can only store a maximum of 9 waypoints, we're going to enter max it as first waypoint. So how do we do this? First of all, we want to set up all 3 INSs at the same time. So we're going to take the selector on the left here and switch that to remote. And we do that on all 3 units. That way, if we enter something into one unit, it's going to automatically be entered in the others. Do note that at the time of the release of this tutorial, that functionality is not implemented in the iniBuilds aircraft, but they will add it with a later update. Alright, next up, we are going to rotate the selector into the waypoint position, and then select the waypoint as needed. So waypoint 0 is always your present position. If you want to enter the first waypoint, rotate this to become waypoint 1. Now, we take the GPS coordinates over here and enter them over here, just like we did with the previous position. So for max it, we got 51, 15, 0, so that's north, 51, 15, 0. Now press insert. Next, we got the longitude, which is 33.7, so we press west, always enter the leading zeros, so 0, 0, 0, and then you got 33.7, like that. When the number is checked in the window, you can press insert, and then I would draw the number 1 next to max it on my flight plan over here. That way, at any later point, I immediately know waypoint number 1 that I entered down here is that waypoint. That's the reason why I want you to put that flight plan onto a device where you can draw in it. Alright, next up comes waypoint number 2, and that's going to be Midhurst. So Midhurst, it says 5103.2 north, 51 03.2, insert, and then at 37.5 degrees west. So west, 00037.5. Alright, and insert. And next, draw number 2 next to Midhurst. Right, then we continue on. Next up, waypoint number 3 is Drake, 5012.6. So that's 5012.6. And the west coordinate for that is 4.6. So 00004.6. Insert. And that's waypoint number 3. Next up comes Systat. Waypoint number 4, Systat, 5006.0. And exactly 0 degrees east, so you can choose either west or east. Let's do it correctly, press clear. So east, 00000, 0. Insert. Alright, so Systat becomes waypoint number 4. Next up, we do not need to enter any FIR boundaries or top of climbs or that kind of stuff. Next up is going to be AirTat. That's going to become waypoint number 5. 4941.0, 4941.0, insert, and now we're on the east, 9.6, so east, 00009.6, insert. Okay, with that, AirTat has just become number 5. So now we move on, and we got Deauville. That's 4918.6, so waypoint number 6. 4918.6, insert, and 18.8 east, 00018.6. Actually, that's incorrect. Clear. East, 00018.8. That's it. Insert. Okay, waypoint number 6 is entered. Next up, we got L'Aigle, Lima Golf Lima. That's going to become waypoint number 7. 4847.4 and 31.8. Okay, and insert. That's number 7. Then we got number 8, which is going to be Sorap, 4831.3 and 38.1. Like that. And finally we got Benar, which is going to become number 9. So that's 4815.2. And east is 44.7. Like that. Insert. The maximum number of waypoints you can enter down here is 9. When overflying waypoint number 9, the aircraft is going to fly back to waypoint number 1. So what we will be doing here is we can see Benar, 26 minutes in flight. So prior to being 26 minutes in flight, which is basically when we're gonna reach Benar, we got to enter the next number of waypoints. So do keep that in mind. Otherwise, overflying waypoint number 9, the aircraft's automatically going to fly back to waypoint number 1. Once that entry is complete, you can switch it back into auto. And now, if that functionality would already be simulated, you would get those waypoint coordinates for every single one waypoint. Unfortunately, not simulated right now, so that's a little thing that iniBuilds still have to do at the time of this recording. Now, provided that the nav ready lights are illuminating already, we can switch the IRS into nav. 1, 2, 3. And now our INS is ready to be used for navigational purposes. Well, that's pretty much it. So our INSs are set up, and the next thing we can do is to set up our performance management system. Now this is a little interesting system. The way that the PMS works is you have to enter some basic data, and then it is able to provide basic VNAV. So let's go ahead and see what we actually need to enter into the PMS. Now, we have to start at the very top with the GMT time. The way we do this is to press the LSK next to GMT, GMT Greenwich Mean Time, also known as UTC in aviation. It may already be populated, but we still need to enter it. So verify the correct time. Right now it's 11, it should be 12:25. Let's go down there, enter the LSK next to it, 1225. You will see the insert light illuminate, so press insert. And that's going to populate the other fields. Now we still need to enter the gross weight, the fuel, and the static air temperature. So let's continue by entering the gross weight. Can find that in our load sheet over here, and that's 160.8. So we go down here, press the LSK next to the gross weight, enter 1608, and you may have to round it, so round it up, 161. Insert. Next is our fuel. For the fuel, we do have 20 tons on board. So let's go down here. Fuel, 20.0. You cannot enter the point, it's going to do that automatically. So the last digit is always going to be after the decimal. So if you enter 200 and press insert, you can see it's going to become 20.0. Next up we need our temperature, which we can just take from the gauge, and that is 14 degrees right now. So SAT, press that field, 14, insert. Alright, and with that we've completed the takeoff initialization page. Next we go on and press forward, and that's going to lead us to the flight setup. Over here we need to select the bottom of descent distance and altitude. So what is that? Bottom of descent is the point where your descent ends. So you normally would take the initial approach fix or your destination airport. So let's go ahead and have a look. Going into the flight plan, we can find our total distance. So over here we got ground distance 652. So the distance to the bottom of descent is going to be 652. Insert. The bottom of descent altitude, you could enter the field elevation. I'm going to go with something a little bit higher, just because we have to set the aircraft up for the approach. So we're going to use 3,000 feet over here. Insert. Now if you want to, make your life easy, you can take that distance, subtract 10 miles, so 642 instead, put 3,000 feet in there, and now you will end up 10 miles before the airport in 3,000. That's quite easy, isn't it? And the bottom of descent speed, in that case 200 knots, insert, and that way we have done our flight setup. Now we go next, and we have to enter our cruising altitude on the altitude field down here. This will always default to flight level 430, but we can see our optimum down here, flight level 370. So let's go down here, and well, our flight plan has us in 3.5. The system tells us 3.7, so we'll probably request 3.7 from ATC. So let's enter 3.70 and insert. And that way, the system now has all the information it needs and should start calculating. Unfortunately, in my experience, it doesn't always do that. So right now, it's not calculating anything, as you can see. That, I consider that a bug. So this should give you your Takeoff Climb distance and time, and then later on also distance to step climbs and to the top of descent. Again, I do consider that a bug right now, but that's the way how you are supposed to do this setup. Okay, so with that, we have talked about the PMS, we have talked about the PMS, and we have talked about the INS, and basically everything is set. So from that point, we can go ahead and start setting our aircraft and our takeoff performance up for today's flight. So I would suggest we are going to go right into the takeoff performance up next. So a couple of things we need to talk about. If you do have access to the official takeoff data charts, you could get all fancy and start calculating reduced thrust takeoffs and so on. We don't have that in the flight simulator. So what we're gonna do here is we are going to use the system provided by iniBuilds for that setup. So let's go right down here and onto the takeoff performance page. On the left side, we need to enter the takeoff gross weight, the pressure, altitude, and the temperature, and the flap setting. And on the right side, it's going to get you all the relevant data for your takeoff. So let's go ahead and start up here. Takeoff gross weight. We just said it's roughly 161 tons. Pressure altitude. You can Google for a pressure altitude calculator if you absolutely want to. Otherwise, make your life easy. Just enter the field elevation. Temperature, we said, is 14, and flaps 14 is also the standard takeoff flap setting. When all of that stuff is entered, if you want to make your life easy, you just press the sync button, it's automatically going to do this. When all of this is entered, hit calculate. You can see that it's now filling out your takeoff data card on the right hand side. This is not just located in your paper flight bag, it's also synchronized up here on the first officer's main panel so that you have quick access to this. So let's go over what we see on the takeoff data card. The EPR is always given as point because it's always 1 point something. So if you're looking at your gauge, always 1 point something. So takeoff EPR 0.643. You can see that it's also, once we press the set box and EPR button, which I'm going to do now, you can see that it is automatically setting those bucks on your gauges. Now, that's the takeoff EPR. After takeoff, we will reduce our thrust to the climb EPR, and the initial climb EPR is basically what we're using for noise abatement here. That's going to be 556 in today's case. So we do have that available as reference down here, but I do like to insert it up here as well. So I'm just taking the center engine and scrolling this down to 0.556, so that I have this as a reminder and as a visual indicator up here for my number 2 engine. Now, for the takeoff, we're still going to use that. For the climb, I'm going to use that. The reason I'm doing this, look at your panel. This is the view you're going to have during takeoff. You can see this and this, but you cannot see this. Unlike in the real world, where you simply look over to the side and you immediately have it. That's why it would be nice to have this on this side, but let's see if iniBuilds is ever going to do that. Alright, so that's the EPRs we have for takeoff and for climb. We also have the maximum contingency and the maximum power in case it is required. Now, maximum continuous is basically what the name suggests. Maximum power is what you can use temporarily in case you get, for example, into wind shear. Unlike modern airliners, if you smash the thrust levers all the way forward in an airplane without FADEC or electronic engine control, you're gonna wreck those engines. So that's the reason you got the maximum power EPR down there. Takeoff speed, self-explanatory. Takeoff flap setting and stabilizer trim, 4.71 units, which we will have to set later on down here. But that's done only later on, after the hydraulics are pressurized. Your minimum maneuvering speeds are also calculated down here. You can set those speed bucks manually, or you just use the automatic set box and EPR function that I've just used. So let's just quickly talk about what we see on the speed indicator. I'm going to do this quick because we will talk about it again before the takeoff. So here's your V1 and VR. Here's your V2 plus, here's your V2. Down here is your flap 10 speed, flap 4 speed, flaps up speed. So once you're faster than this, retract the flaps from 14 to 10. Once you're faster than this, 10 to 4. Once you're faster than this, 4 to 0. And that's your minimum clean speed. And that's the takeoff box that we have just calculated over there. So with all of that done, we have completed our pre-flight procedures. Now, this took us, an hour and 24 minutes in the tutorial. This will get much, much quicker when we do it again later on. So once you're used to the plane, you can do this in 25 to 30 minutes. So yeah, practice, 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 practice. That's the important thing over here. Now, since we have completed our pre-flight procedure, this would now be the time to read the before start checklist. Once again, at the beginning of the video, I do explain where to find the before start checklist, so do have a look in that, and then once you have found it, we can go ahead and read that list. So the pilot function line before start checklist goes as follows. Flight director checked, it's checked. Instrument comparator checked, remember we've done that. AFCS warning mode annunciators checked, we've done that. Radios checked, they do indicate correctly. Radar checked, not gonna do that in here. And GPWS is not installed on this plane. That's pretty much the only difference I see from this checklist to the iniBuilds version. So, before start checklist. Oxygen mask and interphone, checked, we've done that. MSUs, those are the mode selector units for the INS. The checklist says align, but since our alignment is already complete, we already have them in nav. Compasses, MAC, and synchronized. Overhead panel checked, anti-skid checked and off. Emergency lights and standby power, those are those two in the front over here, are armed. Cabin signs on. AFCS panel is checked, that's the auto flight control system panel. That's all checked. Flight instruments checked, all indicating correctly. Annunciators checked. Engine instruments checked and reset. So brake system, normal. Radios and radar are all set. INS is checked and set. Throttle quadrant is checked, namely flaps up, spoilers up, thrust levers idle, and trim at 0. Okay, landing gear, down 3 green. Trim, 0. Here, here, and here. So, that basically concludes the stuff that we're doing at the front. Now we're going to the back, to the flight engineers panel. So next up is fuel quantity, and that's 20.7 tons. Oxygen mask and interphone is checked. Fire and overheat protection, we've done that earlier, is checked. Electrical panel is checked. Battery switch on. Fuel panel checked. Remember all the tests we've done down here and on the tank 3As. And pressurization. So we're looking at set over here and over here. Also set that QNH real quick. So here, and normal down here. And logbook is checked, and that's the before start checklist complete. So with that, we have done everything that we had to do down here in order to prepare our airplane. From this, we're going to go into the before start procedures, then the pushback and the engine start. So at this time, we would call air traffic control for our clearance for startup. If you are at an airport where pushback clearance is needed separately, then you would wait until you have carried out the procedure before you get the pushback clearance. That's so that you are able to commence the pushback immediately when the clearance is received. Okay, so let's go ahead and get started here with the before start procedures. And that mainly starts on the flight engineers panel. So let's move right back here. If you are using GSX, now is a good moment as ever to request pushback and departure so that GSX gets you ready to go. If you haven't started the APU yet, do start the APU now. Remember, that's master power on, hold the start light until the do not load button goes out. When the APU has started, make sure that the generator field flow lines are on and that the AC meter gives you frequency and voltage. Now when that is checked, frequency, voltage and the flow lines on, then you can switch off the external power and disconnect the external power through the paper flight back, like this. Now external power is removed. Next up, we are going to go up to the ECS panel, and we are going to set our air conditioning. So the way that we do this is you can leave one pack on, and you gotta have the cross bleeds open. So bleed is on. APU bleed is also on, and the cross bleeds are open. That way air can flow from here up here to the engine starters. And only single pack on, otherwise we do not have sufficient bleed air available. Okay, so let's go for it. The door lights are all out over here. Galley power is going off. Fuel pumps, we only turn a single fuel pump on over here. So only a single fuel pump on. And then we make sure that the cross-bleed valves, all three, are open. The reason we do this is so that all three engines are supplied by a single pump. We do not want to turn on more pumps because the APU is not very powerful, and otherwise we would not have sufficient electrical power available. Okay, and with that we have finished our procedure on the flight engineers panel. Now we move back to the front and we set up our flight deck. So anti-collision light is coming on, and the transponder is going into altitude off. And if the INS alignment hasn't been completed previously, then we ensure that the INSs are switched into the nav mode right now. And that's pretty much everything complete that we have to do up here. So now let's go ahead and read the start checklist, which is MSU nav. So that's the mode select units, all three of them in nav. Anti-collision light on, park and brake set. And now in the engineers panel, electrical panel checked. That is verifying that the galley buses are off and that the APU is connected to the electrical system. Then you have fuel panel and gross weight checked and set. Over here we make sure that the gross weight is set up here, which you can do with a single press of the button in the middle. That synchronizes the gross weight. And then you only have a single AC fuel pump and the cross feeds are open. So fuel panel and gross weight checked and set. APU min mode, that's over here in minimum mode. And pack flow, one on, and that's only a single pack on up there. The other two, as you can see, are off. Alright, and that's the start checklist complete. So, with this done, we can go ahead and release our park and brake in order to start the pushback. Now let's have GSX do its thing down there. Pushback is starting. Okay. So let's go ahead and start the engines. There is no FADEC in this aircraft, so the engine start is a complete manual start procedure. Now, let's go ahead and talk about it before we do it, and then we have 3 attempts at practicing it. So we start with the engine to ground start switch. That's the one up here. Push that on. Then observe the ground start release push light on the top up here coming on. That button is used to abort the engine start if needed. And observe that the ground start valve open light does come on. If there is no N3 rotation, N3 is down here, within 30 seconds, push the ground start release push button to abort the engine start. At 20% N3, we turn the fuel on. At 55% N3, the ground start switch should release and the push light goes out. And then we check the stable engine parameters, which should be 23% N1, about 350 degrees TGT, 60% N3, and the fuel flow at 1,500 pounds per hour. Remember, we are using kilograms here, so about half that. Okay, let's go ahead and start an engine. So the sequence is 2, 1, 3, always. Then we commence engine 2 start. Push light comes on. N3 is increasing within 30 seconds. Now we are monitoring. N1 is increasing. And at 20% N3, we are going to switch the fuel on. So here's 20%. Fuel on. TGT starts rising as we have ignition. And the fuel flow is about at 750. Remember, it was supposed to be 1,500 pounds. This is kilos right now. It's about at 750. Alright, and with that, our engine is starting. At 55%, we are expecting starter cutout. And this is looking fantastic. That's 55, the starter is cut out, so now we can start engine number 1. Again, the start release push light comes on. N3 is rising. N1 is rising. Here's 20% and switch on, respectively fuel on. If any of the numbers starts exceeding their limits, push the engine start release switch up here, and that is automatically going to abort the engine start sequence. Alright, here we go. Both are going out, and that's it. Okay, so we have one more engine to start, so let's start engine number 3. Up here. And there's N3. Now, if you take a close look at the switch, at the fuel and ignition switches, you will see that there is an enrich position. This is currently not simulated by iniBuilds, but what this would do is to enrich the fuel mixture in the engine, and that would accelerate the engine start procedure. Initially, when the Tristar came out to the market, that was rather limited and only allowed under certain circumstances, but it was later determined that this could be used without any restrictions, so that way you could accelerate the engine start procedure. Now, this is not simulated by iniBuilds, but just know that it actually does exist in the airplane. Alright, and here we go, that's the third engine start now completed. So that's 3 good starts. Let's set that park and brake so that GSX can start disconnecting all their stuff, and then we can go right into the after start procedure. Okay, so after start procedure. For that we go back to the flight engineers panel. So if the APU was used for the engine start, which it was, we are going to connect the generators of the 3 engines, which is now done. Check their voltage and frequency to look good, which it all does, and then we're going to trip the APU generator breaker. Field breaker can stay on, but trip the APU generator breaker. Now, from there, we are going to move to the APU panel. APU bleeds. APU bleed air shutoff valve unlatch. APU stop button down here, press, and this is going to initiate the APU shutdown. And after 2 minutes, we're going to turn the APU master power switch off. Basically, I would delay that until we're reading the after start checklist. By that time, you basically have 2 minutes. So now let's go on to the engine air control panel. Basically, we need to put this in a typical flight configuration now. So we check that the engine bleeds are providing bleed air and that the isolation valves are open. We verify that the cross bleed valves are open, and we can turn the pack controls on for all 3 packs. Finally, check that the flow bars are closed for the hot air and the isolation valves, and that way we are now all set up for our air conditioning by the engine. So from here we move on to the hydraulic panel, where we are going to switch the ATMs into the on position. Observe that the ATM RPMs are rising, which they are, and then we can switch them back into the auto position. We verify that any warning lights on the hydraulic panel are out. Then we move down to the electrical panel, and we turn on all 3 galley powers. We ensure that all the generator fields are closed, all the generator breakers for the main engines are closed, and we verify that the temperatures are all within limits. Finally, moving down to the fuel panel, we turn on all the tank pumps, then we can turn off the crossfeed valves. So, to verify, because it's always easy for me if I have a certain flow in my mind. The first thing you do is to put the engine generators online, and then you trip the APU. Now, after that, you shut down the APU, then you go to the engine bleed controls, left to the hydraulic, down to the electrical, down to the fuel. So basically, generators online, APU offline, ECS, hydraulic, elec, fuel. And that's it. That's about as easy as this is. Now 2 minutes are over, so we can turn the APU master power switch off by now. Alright, and that's what the engineer has to do. So let's go back to the captain's seat and do the captain's flow. We're starting on the overhead panel by turning on the air data and sensor heats. Verify that the windshield heat are on and set the engine and wing anti-ice as necessary. Engine anti-ice is necessary when the outside temperature is plus 10 degrees. So right now we're at 14, we don't need it. But when the outside temperature is plus 10 degrees or less and there is visible moisture. So that could be very low clouds, below 1,000 feet. That could be rain, fog, that kind of stuff. Then you would need engine anti-ice. Wing anti-ice, basically not used, because if you de-ice the airplane, you are not allowed to use wing anti-ice, and otherwise you would only need it in flight. Okay, so then we switch the engine start switch into the both position, and we go down, set the stabilizer trim, which we can get from down here, 4.71 units. So stop trim 4.71, flaps into the takeoff position, which is the third position, 14. Like that. And we verify that the flaps are actually extending into that position. Then we cycle the speed brakes and observe them rising down here. Like this. Looking good. And after that we are going to test the flight controls, which again we are going to verify down here. So, full up, full down, neutral, full left, full right, neutral, and the rudder, full left, full right, and neutral. Okay, when all of that is done, we are going to do the next checklist, which is the after start checklist. And that is engine anti-ice off, alpha, pitot and windshield heat on, start ignition, both, annunciators down here checked. And then for the flight engineer, where we got the hydraulic panel checked, which means ATM's auto, all the warning lights out. So hydraulic panel checked, electrical panel checked, generators are online, APU is offline, and the galley power is on. Fuel panel checked, all the fuel pumps are on and the cross feeds are off. Fuel control amplifiers, that's down here, are guarded and unlatched. And APU is shut down, and at this moment, if you haven't turned the master power off because of the 2 minutes, you can turn it off now. And finally, annunciators check, which is up here, and that's the after start checklist complete. Alright, and for the time being, this is pretty much everything that we actually have to do on the flight engineers panel. You can see it is a little bit of stuff that you gotta get yourself familiar with, but overall it is quite alright once you get the grip of it. So let's now go ahead and start the taxi. Now there is quite a bit of theory to talk about before starting the taxi. Most importantly, when we look at the design of the Tristar, we'll notice that the main landing gear is located very far aft of the plane. Like on most aircraft, gear would be somewhere here in the middle of the fuselage, but the heavy weight of the aft engine means that it has a landing gear that's located very far aft. The nose gear is also located very far behind the flight deck. That's really like 5 meters or something. So we got to keep the main gear on the taxiway center line while keeping the nose gear on the paved surface. And while we ourselves are sitting far in front of the nose wheel. That means this airplane requires a lot of oversteering technique. So let's go ahead and start taxiing, and then I'm going to show you what that means. On a very tight turn, you might have to steer yourself sitting here over the grass, so over the edge of the taxiway, in order to keep the nose wheel and the main wheels on the taxiway. Alright, let's go ahead and have a look at what that looks like. We switch the taxi light on and we switch the runway turn-off light on, then we can release the park and brake. You will notice that at light gross weights, the aircraft is going to start rolling with the engines in idle thrust like this. At heavier gross weights, you may have to apply a little bit of thrust, but you shouldn't apply more than 60% N3. So no more than roughly this. 70% occasionally acceptable, but not for too long, because you got some pretty strong engines here. Okay, brake check. And we can feel that the airplane response is normal. And with that, we're up and on the way. So let's talk a little bit about taxi speeds. On a tight turn, a maximum speed of 10 knots should be used in order not to overstress the fuselage during that turn. On an apron, you should taxi a maximum of 15 knots to have plenty of time available to observe any possible obstacles. Now, on a long straight taxi line, 30 knots can be used, and when backtracking a runway, a maximum of 50 knots can be used. Now let's talk about oversteering. We are entering the first turn, we go nice and slow, and you can see how far I'm taking the flight deck over the center line. When you are turning the plane, try and imagine where the turning point of the plane, aka the landing gear, is located, and then steer your airplane to position that turning point onto the taxiway center line. This will take a little bit of practice at first, because you are sitting so far in front of the nose wheel and because the main wheels are located so far in the back of the aircraft. Once you get the hang of it, Tristar is a really easy airplane to taxi, but you really got to get the hang of it. In order to demonstrate this a little bit more, let's do a couple more turns over here, switching between taxiways Bravo, where we are on right now, and taxiway Alpha, which is parallel to us. So again, take it nice and slow. You don't have a ground speed indicator here, but you can cheat. I'm going to show you in a few moments. Nice and slow. Now steer the flight deck completely over the line, and then slowly start turning the aircraft. From the outside, this is what it looks like. You can see the main wheels pretty much on the center line here. Nose wheel is really oversteering quite far, and the flight deck is overshooting a lot. And that is how you taxi the Tristar. It's really different from what you're used to from many other aircraft. Again, same thing over here. Imagine the turning point of the aircraft. Position that turning point, which is the main wheels, on your center line. And this is what it looks like. Once you get the hang of it, it's quite easy, but it does take a little time to actually get that hang of it. Let's do one more. Over here, going to the left. Again, we are quite far in the front. Do control your speed, you're sitting rather high. And here we go. Okay, one more going to the right, and then I think we have it for the turns. Again, keep it nice and slow. Use your best judgment for the speed. And here we go. Nicely to keep the mains on your center line. Or rather, keep the center line in between the mains. Alright, so, as mentioned earlier, you do not have a ground speed indicator anywhere immediately visible within your panel. But what you can do in order to get yourself comfortable with judging the ground speed of the Tristar, you can look down here and switch the INS mode selector all the way to track and ground speed. And that way, you are actually going to get some data, or at least you're supposed to. I think we got to do track change, 0 to 1, direct. Now you're getting the ground speed. That shouldn't be necessary, that is a bug. But right now you can see we're going 18 knots. Looking outside, that's what 18 knots look like. Memorize those speeds. At the end of the day, you're not supposed to taxi Tristar with a look down at the INS. You are supposed to taxi it with a look outside the window. So do start developing a feeling for that aircraft. And that way you will be able to control her pretty nicely once you are used to the height at which you sit above the taxiway, and therefore the associated speeds. Like right now, I would say we're approaching 30, and looking down here, yep, that's 25 knots. So keep it nice and slow all the way through your taxi. Now, when you have time available during the taxi, I would recommend to review the takeoff briefing. This is not official procedure, but you gotta fly a lot of stuff based on what you see down here, so do take some time. Here's the most important stuff that I would recommend you to review during a taxi. It's the takeoff speeds and thrust setting, so 34, 34, 47, and your thrust setting, which you got a reminder for up there. Now, for our standard instrument departure, we are going to fly straight ahead to join the radial 239 outbound London till 5.5, then left turn QDR 160 outbound from Burnham until 12 dB London, and we gotta switch the frequencies while we're on this leg over here. Gotta keep that much in mind. Now, engine out, straight ahead 25 miles, climbing 3000 with an MSA of 2100, and that's like the most important stuff that you gotta memorize for flying the Tristar. Overall, not too difficult, but a little bit of stuff to have in mind. Now, when all of that stuff is done, we can go ahead and start with the before takeoff checklist, which is brake system checked. Remember, we did that when we started taxiing. Continuous ignition on or off. We're gonna keep it off. The only time when you would turn the continuous ignition on is when you would have very strong precipitation, or when you got like snow or slush or something that could interrupt the ignition process within the engine on the taxiways and runway. So in most conditions you will have the continuous ignition off, really only snow, slush, or when it's raining like really strongly. Okay, let's continue with the checklist. Flaps and slats, 14 and 14. Stabilizer trim, 4.7 units set. Flight controls checked. Flight and nav instruments are set for departure. Takeoff data checked and set, so we have the box. Briefing completed. See, the briefing is even in the checklist. Then ATMs, auto, APU, off, and cabin crew alerted, and that's the before takeoff checklist complete to the line. Now, one last thing that I want to show you for taxi before we get into the before takeoff procedure. That's where to hold short. So we got a hold short at runway 27 left. You can see the hold short line over there. Many flight simmers would hold short in a position like where we are right now. Let's see that from the outside. That's a lot of distance, isn't it? The reason for that is the cutoff angle. So the area you cannot see in front of your main panel. You're sitting where you are, you're looking through this, and you see that runway 27 left sign. Looking outside, that entire area down here, you cannot see from your flight deck. But since we may have a taxiway behind us, since other aircraft may have to taxi behind us, we have to taxi forward until we are actually close to the hold short line. How do we do that? Well, the easiest way is to just look outside to the side a little bit. You can see there's the line. Let's taxi all the way until the line is like over here at the beginning of the paper flight back. Like this. Looks close, doesn't it? Here you can see, now we're actually at the line. But that is how you hold short of a certain feature on your... that is how you hold short of a certain feature when you are instructed to hold short somewhere. So really not all of that easy, but absolutely required. Okay, so let's go ahead and talk about our takeoff. So we are first of all going to talk about the theory, then we're going to put that into practice. Now, the takeoff in the 1011 is a very manual thing. You got to set your thrust manually, you do not have an auto thrust for that, and you got to control the entire airplane manually. So let's start with the takeoff run. At the beginning of the takeoff run, apply a little bit of nose down elevator in order to improve the effectiveness of the nose wheel steering, which is going to decrease when your engines are pushing the nose up when takeoff thrust is set. Remember, the engines are located below the center of gravity of the aircraft. So we counter that with a little bit of nose down elevator. Stabilize the engines at roughly 60 to 70% N1, and thereafter we are going to set takeoff thrust. What I found easiest to set takeoff thrust is to increase the thrust lever rather rapidly, and when the EPR approaches the target, just keep pulling back until the EPR stabilizes, and then do a little bit of fine-tuning to get the takeoff thrust to somewhere within the target EPR. Now, today's takeoff EPR is 0.643. Whether it's at 0.635 or 0.650 is not going to make that much of a difference, so just set that EPR somewhere around 0.643, slight differences can be accepted as long as we are not exceeding that maximum continuous EPR down there. Now, or rather that maximum structural EPR of 656. Alright, now we are going to accelerate. We release the control column back into the neutral position at 80 knots. Then we reach V1 and VR. We rotate to an initial pitch of about 15 degrees or whatever is commanded by the flight director. Once we're safely airborne and climbing away and we observe a positive rate of climb on the altimeter, not on the radio altimeter, on the altimeter, then we're going to retract the landing gear and we are going to maintain a speed of about V2 plus 10. So here's V2 plus 10, so about 160, by pitching the aircraft until we reach 1,000 feet above the ground. When reaching 1,000 feet above the ground, we pitch down about 10 degrees-ish and start accelerating, and at the same time we also set the climb EPR that we've set up here. Now, when the speed is greater than V2 plus 10 and accelerating, we retract the flaps from 14 into 10, so we retract them 1 notch until we're passing that speed buck over here. When passing that, we retract the flaps from 10 to 4, keep accelerating until we're passing this speed buck. At this buck, we retract the flaps from 4 to up. And then we maintain the up speed until we're at 3000 AGL. Now, the pitch may be rather high, especially when you're flying Tristar on a short-haul flight. Remember, we are sitting in the long-haul version of Tristar here, so the maximum takeoff weight is really high. You are flying at a very low gross weight. Okay, so that's the takeoff sequence. If you have a speed limitation that doesn't allow you to accelerate to the next setting, let's say for example we had a 200 knot limit, then we would stay in flaps 10 at this point until we are allowed to accelerate here. And only once we're allowed to accelerate to the next buck, only then we are going to retract the flaps into the notch appropriate for the buck. So again, accelerate here, retract flaps from 14 to 10, pass this, 14, oh, correction, pass this, 10 to 4, pass this, 4 to up. And this is the minimum clean speed, the minimum speed that you're allowed to fly with the flaps up. Alright, for our navigation, once we intercept the radio 239, we are going to be able to tune VOR mode over here and then engage the autopilot. I would recommend flying the departure procedure by hand because it is much easier doing all of that without having to constantly worry about autopilot modes. It really is. Okay, and once we're established on a nice leg over here, we can engage the autopilot, do all that cleanup work. Now, for systems control, there is only one thing that needs to be done quickly on the flight engineers panel after takeoff, and that is switching on the packs. The takeoff is always done with a single pack only, so packs 1 and 3 are going to be switched off for the takeoff. The only thing you need to worry about on the flight engineers panel in the entire takeoff sequence is turning those packs on once you're airborne and climb thrust is set. Apart from that, nothing to do back here. The flight engineer would be sitting facing forward, controlling your engine thrust to make sure that the thrust is set as accurately as possible. Alright, and that's pretty much everything there is for the takeoff theory. So let's go ahead and talk about the lineup procedure. This procedure is done as soon as you get lineup clearance from ATC. So that may include takeoff clearance as well, by the way. So let's go ahead and talk about the lineup procedure. This is basically all on the front panel over here, except for the packs. So anti-skid, on, auto brake, takeoff, strobe lights, on, and once the takeoff clearance is received, we're also going to turn on the landing lights. Continuous ignition as required. You can turn it on at this point if you absolutely want to. So let's go ahead and turn it on today, just so that we think of it later on in the tutorial. Verify that the probe heats are all on. Then we just move down, switch the transponder into TARA, and select the weather radar to WX plus T. And that's the entire lineup checklist complete, or rather the lineup flow complete. From our side, one more thing to do on the flight engineers panel, that's to select packs 1 and 3 off. Okay. Alternatively, you can select all packs off, but that is usually not required for takeoffs in the TriStar. Alright, and with all of that done, let's do the before takeoff checklist from entering runway. So that's landing and strobe lights on, any skid, on, alpha heat off lights out, transponder TARA, and pack flow 1 on. And that's the before takeoff checklist complete. So let's go ahead and line up on that runway. Lineup technique, let's quickly talk about that. Many flight simmers have a tendency to follow the yellow line that is designed for vacating the runway for the lineup as well. That wastes a lot of runway space. Do not do that. Much rather what we do is to aim to line up at a 90-degree angle. You can even do this when you are taking an intersection. You can just turn a little bit towards the side of the runway and try to make the angle as tight as possible. Then we are using the oversteering technique to the absolute maximum in order to verify the lineup uses as little distance as possible. So let's go ahead and do that. We steer the flight deck straight across the center line, and only now we start aligning the airplane with that runway. Now, doing a tight turn may require a little bit of thrust. Be sure to keep your airplane rolling. And here we are. That's our lineup complete. If you see this from the outside, you can see we started here, we are now here. On many airports, if you follow that yellow line, you would end up somewhere here, which wastes, 50-60 meters of runway, which may be all you have left for your stop margin. So always be a little bit careful when you are lining the airplane up to make it as tight as possible in order not to waste any runway space. Alright, so that much for our lineup. I'd say we are now going to go for the takeoff. So let's start by noting the takeoff time. This is going to be important for your flight plan later on. So it's 12 right now, 13:12. Write that down if you can, if you have the time. Okay, let's start. We are going to keep on the brakes, and we are going to start just putting our thrust levers into a straight position, which is roughly going to get your engines to 60% N3, or correction, 60% N1, where they are going to stabilize. Thereafter, set takeoff thrust. So levers forward. The EPR is approaching the target. I'm slightly reducing it, and now we're looking for a 643. Here we go, 645 is good as well. Brakes released, takeoff. A little bit of forward pressure on the control column. 80 knots. V1 rotate. Rotate to about 15 degrees pitch. A little bit more may be needed if you are lightweight. Alright, and gear up. For us, 20 degrees pitch seems to work quite well right now. Now we're waiting to intercept the radial, and we're monitoring the altimeter. And when we're at 1000 AGL, which we are now, we're going to reduce thrust to the climb setting, which we've set on the middle instrument there. Okay, we start accelerating. Flaps 10, flaps 4. And flaps up. Okay, maintain the upspeed until we're at 3000 AGL. The main reason to do this is to assure track keeping, because it can be rather difficult to navigate that aircraft. Okay, here comes the radial. Let's intercept that. Okay, we're at 3000 AGL, so we can continue accelerating towards 250 knots. Here we go, and here we are, maintaining 250. So let's put that autopilot on. VOR mode, speed hold mode, and autopilot on. And here we go. Do note that sometimes the modes like to trip off, so when the autopilot is engaged. Alright, we're reaching 5.5 DME from London, so let's make that left turn on a heading of 160. Come on, heading mode on. 160 is selected, and we are just going to continue that climb. You can give me ES hold, please. So just continue that climb all the way to cruise level to make it nice and easy. That's going to be level 370. Okay, if your speed is a little off the target, you have to use vertical speed mode. You cannot change the ES directly. Right now you can see it's accelerated a bit. Let's help it. Once we're in the air, we can use thrust mode in order to have auto thrust automatically select the climb EPR. And now we are basically going to navigate along the SID. So we need 160 outbound from Burnham. We overshot a bit because the plane accelerated, that's expected. So down here we got the end of the ADF needle, and navigating on an ADF, pretty easy. If you're facing the end of the needle, or if the end of the needle is up, you're always pulling it along. We want this to be here. So we're going to turn a little bit further left in order to have that needle move along quickly. Now, at 12 DME London, we're going to intercept radial 1 or radial 010 inbound Midhurst. So let's select 010, correction 190, it's inbound. 190 over here, and tune Midhurst 14.0. Like this. Alright, and do keep an eye on what your airplane is doing, we don't want to be fucking this up. Alright, here comes the radial, so let's press VOR in order for the airplane to follow that radial inbound Midhurst. Passing 10,000, we're gonna select that vertical speed down. See how I saved myself from losing a bit of speed here? So passing 10,000, we're gonna select the vertical speed somewhere down and accelerate to 320 knots. Which we can set with the speed bug up here as well. So we're now inbound Midhurst, and we are about to overfly max it. So let's go ahead and transition from VOR navigation over to INS navigation. Remember the numbers on your flight plan? Basically how max it was number 1, which we've basically overflown already. So Midhurst is number 2, waypoint number 2. So what we're gonna do is go down here, press the track change button, 0, which is your present position, 2, like this. That looks good. Press insert. And now, when you select INS up here, you can see our INS navigation is becoming available down there. Press the INS mode for the autopilot to enter INS navigation, and now we are correctly following the route from the INS. That's about as easy as it is. Reaching our target climb speed of 320, we are going to select EIS hold, and now the airplane is automatically going to maintain that. Now for common practice, it's good to select 320 up here as well. You don't have to, but after selecting EIS mode, you have to reselect the thrust hold mode so that the airplane maintains the EPR that is required. So, to summarize, we're now navigating in INS, climbing in indicated airspeed hold, altitude is on to level off at our cruising level, and thrust management is on so that the airplane automatically maintains the maximum EPR. So that's a lot of stuff that we had to do over here, but things are going rather quickly when flying an airplane like this, so we had to focus on aviating and navigating first. The third thing we have to do now that we are airborne is to do a little bit of systems handling. So, as mentioned, after takeoff, gonna switch all 3 packs on, verify that they're all on. Then we are going to go up to the orbit, deselect the continuous ignition, and finally move the landing gear lever into the neutral position. That's all you have to do after takeoff. When going through 10,000, you will see all of this becomes a lot easier later on when you get more used to the aircraft or when you don't have to explain that much stuff as I just had to do. So, going through 10,000, the flow is quite easy. We are gonna switch the landing lights off, the taxi and turn-off lights off, and when no more turbulence is expected, we are also going to switch the fasten seatbelt and the no smoking sign off. Yes, this is an airplane of that era. Alright, going through the transition altitude, we are gonna set standard, and we only have to do this up front here. You do not have to set standard back there on the flight engineer station. That is not required. Okay, and that's pretty much everything completed that we had to do now. When all of that is done, let's go for the after takeoff checklist, which is landing gear, up and neutral, flaps and slats, up and retracted, continuous ignition off, landing lights off, cabin signs can either be split, so for example, seatbelt on, no smoking off, or the other way around, whatever makes sense. In our case, we got both off. So cabin signs off, temperature and probe heat is checked on, hydraulic panel, basically make sure that there are no faults, the ATMs are in auto, so hydraulic panel is checked, fuel panel. You got all pumps on, and the trans feeds are off, checked. And ECS panel up here, making sure that the cabin pressure differential is building and the cabin is climbing, and that is also checked. And that's the after takeoff checklist complete. Now, when we're in the air, you can take the ground control switch that off, down here, and that's it. With that, we've safely made it out of London, we are navigating on the INS, and we are now up and on our way. But don't think that things are gonna get easy just yet. No, there is a little bit more stuff that we will have to do. So first of all, we're climbing. Getting colder outside, so at some point, eventually, we have to switch on anti-ice. How do we do that, and what type of anti-ice do we use? When the TAT is getting plus 10 degrees or colder, until minus 40, and there is visible moisture that you're flying through, so that could be clouds, fog, that kind of stuff. Then we turn the engine anti-ice on, up here. Engine anti-ice, 1, 2, 3, that's it. You can use continuous ignition if you want to, it's not required by the book. Switch it off again once you're out of the icing. Wing anti-ice is only used when ice is actually building up on the plane. So engine anti-ice is used preventatively, to prevent ice from forming. Wing anti-ice is used after ice has already formed in order to remove that ice. As you can see, you can't really see your wings from the flight deck. But what you can see is what you gotta use. And that is most importantly down here, the transition to the windscreen as well as the wiper. When ice is building on there, then ice will also be building back on the wings. That's a good moment to turn wing anti-ice on. Keep it on for about 30 seconds, then turn it back off again, so that the ice is immediately removed from your wing. The reason you do this, and the reason you don't keep wing anti-ice on all the time, is if that area, the leading edge, is heated by wing anti-ice, and water drops onto the wing, then normally it would freeze immediately on the leading edge. So that when wing anti-ice is turned on, the ice melts at the bottom and immediately flows off the wing and flies away. If you keep the wing anti-ice on all the time, that water could stay liquid when it hits the leading edge, flow onto the upper surface of the wing, where there is no anti-ice provided at all, and then freeze over there. You don't want that. For that reason, use wing anti-ice as an anti-icer only, not as a de-icer. Alright, now we are climbing and we are accelerating. You can see our Mach number is constantly increasing as our airspeed is increasing. Eventually we need to transition to constant Mach, and we do this at 0.82. So when you reach that, select Mach mode, reselect thrust management mode as that trips off. And now you can see 0.82 Mach, and now the airplane is going to maintain 0.82 Mach in the climb. Or at least it should do that. You can see the iniBuilds is still a little, well, not perfect there, but it's roughly going to maintain the Mach number throughout the climb. Every 10,000 feet in the climb, we should move to the Flight Engineers panel and cross-check our pressurization. So what do we want to see on that gauge? The cabin differential pressure, so the difference between the pressure inside and the pressure outside of the aircraft, needs to increase. At 10,000 feet it's roughly 4, at 20,000 it's roughly 6, at 30,000 roughly 7 psi. That thing needs to increase. That large thing over here is your actual cabin altitude. That needs to stay below 10,000, which is right the bottom position. So that way, that thing about 7 or 8,000 feet during cruise is normal. So to summarize, differential pressure needs to increase, cabin altitude needs to stay below 10,000. All of that is controlled completely automatically. If that thing is not pressurizing properly, there's two possible reasons. Either you do not have bleed air available in your packs, then cross-check that the engine bleed is on and that the lines are connected so that the packs over here are getting that bleed air. The other reason is that you may have your outflow valves controlled manually. Make sure that the mode selector is norm and that the manual control switches are not illuminated, so they are unlatched. That's the latch position manual. That can cause trouble if you don't want to operate these. Make sure that they're in automatic. And that's pretty much everything there is at this time in the flight. Now, as we're climbing, as we're getting to higher altitudes, there's a couple of things that we got to keep an eye on and that we can do already. The first thing is always your navigation. Always know which waypoint you're navigating to. When you're approaching waypoint number 9 and you do not do anything, the airplane is just going to return to the first waypoint. It'll fly a 180-degree turn, fly you back to the first waypoint. That may be problematic, especially if you don't have an ATC clearance for it, or if you do want to reach your destination. So be a little careful there. Always know the numbers. If you have conventional backup available along your route, use it by all means. And what is the autopilot doing here? You're not supposed to do that. Alright, I tell you what, let's change that navigation. Let's fly direct to waypoint number 4. Looks like it's done something strange here that it was not supposed to do. What are you doing? Okay, I'm gonna help it a bit here. We want to be climbing, we want to do that at 2,000 feet a minute, please. Just gonna help it a bit to get back to Mach 0.82. So of course lovely when it fucks up like that in a tutorial, but so if the airplane does do strange things like what it's just done, there's usually two possibilities. Number one, you've entered a waypoint coordinate incorrectly. That shit can happen. To fix that, you can simply fly direct to another waypoint. So press the track change button up here. Let's say we want to fly direct to waypoint 6. Enter 0, then enter 6. Now you see 0 to 6. 0 is always the present position. 6 is waypoint number 6. Press insert, and now we're flying direct to that waypoint. Alright. So, still climbing. That's good. Can keep it in vertical speed mode if required here. Just remember, the moment you go back to Mach hold mode, you also have to reselect thrust mode. So we're now at Mach 0.85. That's rather fast, but 8.5 is actually the fast speed schedule of the plane. There's 3 schedules: minimum, econ, and maximum climb. Let's talk about what they are. If you want to do a minimum speed climb, you do 300 knots and convert to Mach 0.80 in the climb. Economy is usually 320 knots and Mach 0.82. Maximum is 350 knots, Mach 0.85. So accelerate to whatever speed you need using vertical speed mode, and once you're there, press the Mach mode, reselect your auto throttle to maintain your climb EPR, and then the airplane is just going to maintain that. Right, now we have 1,000 to go, so let's go to vertical speed mode, 1,000 feet a minute, and now, in order to maintain that speed, we're going to go to auto thrust. You will see that this, by default, just flies whatever speed you've indicated there. But we want to maintain a certain Mach number, which is 8.5. Now let's go ahead, just set that back a little bit in order to maintain that actual Mach number. So we're at about 280 knots. Let's go ahead and select 280 knots as target speed over there. And that way we just got to work our way out until the airplane has achieved the desired Mach number. Alright, we're leveling off at flight level 370, which is our cruising level. We are settling in on our target Mach number. Let's start slowing down a bit more. We want to fly at 0.85 in the cruise. 8.3 would be econ speed, 8.5 is the fast speed. Obviously we are simulating an era where fuel prices were low, so we do want to fly the fast speed, 0.85. Just set that. Auto thrust is very slow, so it might take a little while to actually assume that speed. Reaching our top of climb, there's a couple of things that we do want to write down. So let's go into the flight plan and start a little bit of paperwork. We're at the top of climb, supposed to have taken 14 minutes. Remember we took off at 12? It's now 30 when we reached the top of climb, so that's 18 minutes. Took a little bit longer, but that's okay. The thing that's a little bit more interesting for us is, of course, the fuel. So write down the top of climb time, 30, and then let's go to the flight engineers panel. Right now we have 16.9 tons of fuel. We're supposed to have 16.1. So we did save a little bit of fuel. Write that down. And then also have a look at the fuel used down here, which is basically 1,300 in each tank right now. So we used 3.9. That means we saved 900 kilos fuel. If we look down here at the fuel that we were supposed to have used. And the difference makes sense. So 900 kilos more on board, 900 less used, makes sense, doesn't it? Alright, and with that we have reached our cruise. We can adjust our speed so that we're nicely maintaining the Mach number we're supposed to fly. And with that we have basically finished the climb portion of this tutorial. So next up we're gonna get right into the cruise. Let's go ahead and talk about everything that we have to do while cruising in the 1011. The first thing is always to know your INS sequences. So we're navigating from waypoint 6 to waypoint 7 right now. Let's go ahead and actually start filling in further waypoints. So first of all, we are going to put the INS back in remote control so that we're updating all 3 units. Next we select the waypoint up here, and we gotta take out that flight plan once again. Now remember, we wrote down the numbers, and that way we know that the current waypoint number 9 is Benar. Now Benar is right up here. So what we want to do is to take that selector wheel, that one, and rotate it back to waypoint number 1. Okay, so let's go ahead and start filling out waypoint number 1 with the first one after Benar. So that's going to be Vanat. So that's going to be north 4750.2, insert, east 00055.4. Actually that's incorrect. East 00054.4. Make sure you get those numbers correct, like this, and insert. Now waypoint number 1 is filled in again. Let's continue with waypoint number 2. And that's going to be Amboise. That's going to be at north 4725.7, insert, and east 00103.9, insert. Okay, waypoint number 2 is in. Next up, waypoint number 3. So that's going to be Sopil 47015, insert, and east 1033. Like that, insert. That's waypoint number 3. Now just a quick check. We are navigating waypoint 6 right now. We must not override any of the waypoints currently in use. So we can override waypoint number 4 and number 5, but not number 6. So let's go ahead and enter Balan, which is going to be 46310 and 1020, like that. Waypoint number 4. Then we can also enter waypoint number 5, FPOC 45285 and 1226. Like that. And that's waypoint number 5 now entered. Now, as soon as we pass waypoint number 6, you will see this is going to change to read 7 on the left side and 8 on the right side. What's happening there is that the left side is the from waypoint, the right side is the to waypoint. So currently we're flying from waypoint 6 to waypoint number 7, and if we rotate this to distance and time, you can see we've got a distance of 6 miles to go and 0.7 minutes. The alert light illuminates as soon as you have 2 minutes from the next waypoint, and you will see that that alert light is doubled down here on your HSI. So when the alert light comes on, it tells you you have 2 minutes to go to the target waypoint, and then it flashes when you have half a minute to go to the target waypoint. That's to draw your attention to what the airplane is doing at that time. Now you can see it's sequenced, and now it's flying from waypoint 7 to waypoint number 8. That means we can also fill out waypoint number 6 already, which is going to become Narak. So that's 44177. And east 1449. Like that. Alright, waypoint number 6 is filled in. Do not override the waypoints currently in use, or the airplane may be turning into nowhere. Alright, and when all of that is done, switch the mode selectors back into auto, and that way we are now flying. So if you haven't filled out your flight plan yet, here's what you should do. Enter the takeoff time up here where we actually took off. So we took off at 12 as far as I remember. So we're gonna write 12 in the lower field down here, in actual time overhead. Now we got the time to the next waypoint, and we're gonna add that up and put it into the estimated time overhead field, so in the top one. And that way we are now gonna calculate the entire flight plan with the estimated times overhead. Now this does take a little time, but this will help us navigating the airplane later on, because that way we know immediately at what time we are supposed to be where, and that is easily going to enable us to reach the appropriate or to know when we're going to reach what waypoint, and to know what we got to do when. Alright, so with all of that nonsense added, we got all of that stuff added. I'm just going to go over the entirety of our waypoints over here. So first page done, now I'm doing the second page. You can see there's quite a lot of work in that, but it's necessary. So 2830, I'm just writing all of that stuff down on my paper flight plan. I would recommend you guys to do the same, so that you have a good idea of what you are actually doing. Now, something that you can do when you reach the end of each page, like here, just take the last number you've calculated. For example, here I am supposed to be at time 12. So then write 12 down here, add those up, and that number down that you get down here when adding that and that should be your takeoff time. If it's not, you messed up the calculations. And that way you at least find out without having to recalculate the entire flight plan, but only the page at hand. Alright, so when you've done all of that, you know that every time you overfly a waypoint, alright, that's what I need, that's what I got, perfect. Now, flying along, we should also cross-check our INS navigation with conventional nav aids where possible. Right now we're flying from waypoint 8 to waypoint 9. 8 is Sorab, 9 is Benar. So we're on this leg. That means Amboise is the next VOR we got along our route on 113.7. Let's go ahead and tune that. So 113.7. And that way we can easily cross-check when we are overflying a station. So Amboise, 52 miles. Easy going. Okay. So that much about managing the INS and navigating using the INS. Let's go ahead and talk about other things that we have to do within our cruise. Or at least I'm going to do that once I wrote down the timing or the timestamp here. Okay, so let's go ahead and talk about some of the stuff that, as good pilots, we constantly have to do during the cruise. We're going to start on the Flight Engineers panel. So, a little bit of fuel management is needed in the Tristar. Basically, the first thing we want to know is, do we have any fuel in any of those inboard tanks here? So we got the number 2 inboard tanks, and then we got the tank 3A and tank 1A. If there is fuel in the tanks 3A and 1A, you would press the transfer switches over here to transfer that fuel into the main tank 1 and main tank 3. Now, once those tanks are empty, switch the transfer switches off. Next up, let's have a little look into the fuel architecture and the way that the fuel feeds the engine. So, for that we are going to have a look over here. Now, you can see tank 2, tank 1, tank 3. Now, why are they called that way? Basically because engine 2 is fed from tank number 2. You can nicely see that down here on the fuel panel, if we look at this. So the fuel lines from tank 2 are going down here, interrupted over here, so like this, and then they flow into tank 2. That means tank 2 is feeding engine 2. Tank 1 is down here feeding engine 1, and tank 3 is feeding engine 3. Sounds logical, doesn't it? Tank 1 feeds engine 1, tank 2 engine 2, tank 3 engine 3. The only difference is that those tanks have different sizes. You can nicely see that on the paper flight back over here. So if you take tank number 2, that plus that, it is a lot bigger than tank 1 and tank 3. So what we have to do is to balance the fuel so that we have the same fuel in tank 2 that we have in tank 1 and tank 3. This gets relevant towards the end of our flight because we want equal fuel available for all engines. Now, how do we do that? So first of all, figure out what you have in tank 1 and what you have in tank 3. For that, also check tank 1A and tank 3A, which are empty in our cases. So we know that we got 4.4 tons of fuel in tank 3, 4.4 in tank 1A. That means we basically want the tank 2L and tank 2R quantities to match what we got down here when we add them together. Why is that? Because we want the same fuel quantity available for engine 2 that we want available for engine 1 and engine 3. So basically, this plus this should equal any one of these. So that means we need to transfer a little bit of fuel. Or, to make it a bit more precise, to burn fuel out of tank number 2 without burning any fuel of tank number 1 and 3. How are we going to do that then? So 4.4 up here divided by 2, because we got to split it onto 2 tanks, means we need 2.2 tons in each of these tanks. So what we're going to do is to feed all 3 engines from the tanks 2L and 2R until we see 2.2 tons in each one of those tanks. So to do this, open the cross-feed valves so that all tanks are able to feed all engines. And now, with the fuel pumps here on and the cross-feed here and here on, we switch off the pumps of tank number 1 and 3 so that only tank 2 is feeding all 3 engines. Now, we know that we need to burn, we said we wanted to go to 2.2, so we need to burn 900 kilos of each tank, so 1,800 kilos in total. Let's go up here and have a look at the fuel flow. We're using about 2,200 kilos per engine per hour. Multiply with 3, 6,600 kilos, and we need to burn 1,800. How long is that going to take? Easy mathematics, roughly 15 minutes. So, set yourself an alarm clock for 15 minutes, because in 15 minutes we will have to turn the fuel pumps back on again. By then, our engines will, or our tanks, will be at an equal level. So now, for the next 15 minutes, we will be flying with this fuel configuration. By the way, if you do have a fuel imbalance or anything, you can also rebalance your fuel this way. So generally, make sure the pumps for the tank that you want to empty are on. Make sure that the thrust feeds are on, so that at any time all engines are getting fuel, and then turn off the pumps for the tanks that you do not want to empty any further, so of the tanks with a lower quantity. Alright, and that is your fuel management in cruise. Normally it's just making sure that there is enough, or that there is the same fuel quantity within tanks 2, 1 and 3. Sometimes if you also have to transfer from fuel from tank 3A and 1A using the transfer buttons up here, that becomes a bit more complex, but the ultimate end goal is always to have the same fuel quantity in all 3 tanks, so that all 3 engines have the same amount of fuel available to feed themselves. Alright, so that's rather easy, isn't it? Once you know how the system is working, I really do think that it is easy. It just takes a little time to actually get used to how all of that works. Once you're used to it, very easy. Now that is the main thing that you have to do on the flight engineer's panel in flight. The rest is just checking that everything's operating normally. For example, this is what you're not supposed to see, so a little bug in the iniBuilds there. Also we are cruising in 370, so let's correctly select that up here. And the rest is just monitoring the flight engineer's panel. You can have a look at the cabin temperatures here, which are rather important. Again, Fahrenheit, so you want about 75-ish, like we have in the galley over here. By making sure that the cabin temperature control knobs are about in the 12 o'clock position. Well, and that's everything you need to do in the back here. So, fuel management exercise completed. Let's go back to the flying side of things. Now, we are already navigating towards waypoint number 3 again, and we've only entered waypoints until number 6. So, always a good idea to keep filling up those waypoints. Now, our current number 6 is Narak. That's down here. So we see we got 7 minutes on that lag, 8 minutes on that lag. So we do have a little bit of time available until we actually reach Narak. But always a good idea to keep an eye on this, so that you're not accidentally end up flying back to a previous waypoint. Likewise, flying along, we do have Amboise tuned in VOR1, so let's tune Gaillac on 108.5 in radio number 2 to keep it back up as we're flying along over here. Well, and for the time being, that is everything we got to do up here, so keep a look on our INS waypoints, keep using raw data to monitor where we are flying along, and that way we are slowly but steadily flying along and making our way along our flight plan. Now let's go ahead and have another look at the performance management system. Let's go ahead and select the cruise page and see what we got down here. So right now, what do we see down here? We've got a cruise which is planned at Mach 0.83 for most economy. We're flying 8.5, that is intentional, but this is again telling us the most economical speed there, 0.83, or if we were cruising at a lower level, 285 knots. Now, if we wanted to fly point A3 using auto throttle, simply have to set that airspeed, theoretically. Now, next up, cruising altitude that, optimum altitude is that. When the optimum gets 2,000 feet above the cruising altitude, that's when the step climb is calculated. Then we also see our top of descent down there, and the top of descent is a particularly interesting thing. So remember, always, the top of descent is calculated based on the distance to the bottom of descent that we have specified in the setup pages. So we can see the bottom of descent is defined to be in 345 miles at an altitude of 3,000 feet, and the speed we want to have down there is 200 knots. Based on that, the plane tells us that our top of descent is in 224 miles at time 14:15. So that way, just gotta look over here, 14:15, okay, so we know it's gonna be an hour and 25 minutes roughly to get there. Based on what this thing is thinking. We also do get our true airspeed down here, 481 knots, which is rather useful. Remember, you don't have that anywhere here, and you don't have a speed indication, except for on the INS. If you go to the ground speed prompt, that thing tells you your ground speed, which is 526 knots right now. If you're looking for further information, you can also get your wind data if you rotate the INS to the wind prompt, 048 degrees. Is that correct? No. 336 degrees, 47 knots. That's our wind. Apart from that, what else can you get from the INS? You got your cross track, so over here you could fly offset. That may be useful for avoiding weather. It is not done when crossing the Atlantic, guys. Do not slop when navigating on an INS. The whole reason slop exists is to mitigate against the accuracy of a modern navigation system. INS is inaccurate. So if you end up slopping on the INS, you're only going to make the error that it exists due to the drift anyway larger. Don't want to do that, do we? Okay, so we got 65 miles, 7.4 minutes, inbound to waypoint number 5. I'd say that it's a good moment just to fill in a couple more waypoints, and once we've done that, we are going to talk a little bit more about some of the INS stuff en route that we may have to care about. So I'm on waypoint Narak right now, and Narak is, let's find it in the plan, down here. So thereafter comes Gayak, so let's go to waypoint, let's select the remote controller on all 3 units, like this, and off we go. So waypoint number 6 is the latest we have, so let's go ahead and start filling in waypoint number 7. And just to be sure, we're flying inbound to waypoint 4 right now, so we can't change anything until 3. Okay, so waypoint number 7. That's going to be Gayak, north 4357.2, insert east 149.5. And that's exactly how we don't do it, east 00. 149.5, insert. Okay, that's waypoint 7. Then next up we are flying to Lomra, which is going to become waypoint 8, 4320.7 and east 153.0. Like that. That's number 8, Lomra. Then we continue towards Rokan, which is going to become number 9 at 4244. And 156.8. Like that, number 9. Then we fly on to Puma, which is going to become the new waypoint number 1. And that's at 4220. And 0205. And that's already our star entry. So from there, we are going to resume conventional navigation. Nonetheless, what I'm going to do is enter waypoint number 2, Ellie. And Ellie is going to be at 42079. And to 12.8. Like that. Alright, and that's all we can do because... Actually no, we're in on waypoint 5, so we can add a waypoint 3 as well. And for waypoint 3, since we're on the star already, I'm simply going to take our destination airport. So 41178. And 2047. Like that. Okay, and with that our INS is programmed for the rest and remainder of our flight. Now, if you want to cross-check that you've done all entries correctly, then you can do this by switching into heading mode when you're on a long straight leg. Like right now we know we got 36 miles to run, so let's go ahead, synchronize the heading, like that, heading. So what we can do now is to take all those singular waypoints. So we're navigating from 4 to 5 right now. Let's take 5 to 6, FPOC to Narak. Waypoint change, 5, 6, enter. Distance and time tells me 104 miles over there. And this is actually not how it should work. This should tell me the distance between those waypoints now. So not 104, but whatever is between waypoint 5 and 6. That way you could cross-check that you are that you've entered the correct coordinates. But looks like this is actually not working right now. So let's return to waypoint 5 as we should right now. So flying a direct to track change from 0 to 5. Insert. Now we got that. Looks correct up here. So let's return into INS navigation mode. And here we are, flying nicely along our track again. Okay. So that stuff's done. 24 miles to get there, 2.5 minutes. Now, we are using conventional navigation to back anything up that is located along our route, so that we know that the INS is not completely doing nonsense. And if you're flying very long flights, then at some point you have to consider updating the INS position. How do you do that? So first of all, you do need to know with 100% certainty the location at which you are. Otherwise, if you're updating the INS position, you're just screwing yourself over. How do we know with certainty where we are? Well, use nav aids that are located along your flight. For example, we got Amboise tuned in VHF 1. In VHF 2, we have Gaillac. So, on the en route chart, you can determine the distance of a waypoint, for example of FPOC, from Amboise and from Gaillac. And when you have those two DME readings, you know that you're exactly over at FPOC. Now, what you want to do, therefore, is to wait until you are at the correct position. So until you have identified that position with absolute certainty. When you're able to determine your position with absolute certainty, so when you reach that crossing waypoint, let's say, when you have the correct DME indication, therefore you know exactly where you are, then what you do is to press the hold switch, and that is going to freeze the current position of the aircraft in the INS. It's still going to calculate your further movement, but you press the hold switch, go on the master selector, go to position, you enter the position where you know that you've been at the time you press the hold button, and after that is done, press insert, and then the position is automatically updating itself with the difference that you've already covered in track and distance from the time that you pressed hold, so that it automatically knows the correct position. So let's just assume an example for this. We are receiving Amboise, we are receiving Gaillac. Right now we know that we're exactly over at FPOC. Now you would press the hold key on a position, enter the exact position of FPOC from your flight plan, then you press insert, and that updated the INS position from any possible drift that it might have had. Now you got to try that a couple times in order to get yourself familiar with that procedure. At the end of the day, it's very easy. You just need to be able to determine your actual position with certainty, like you can with the help of a VOR and a DME or two DMEs or whatever there is to ensure absolute position certainty. Alright, so remember we set the 15-minute timer for the fuel? Here it is. Now let's move back to the Flight Engineers panel and check what we got now. So 4.3 is the fuel figure in tank 3 and in tank 1. That means in tank 2, since that thing is split, but feeding the same engine, we want exactly half of what we got in any single one tank over here. So 4.3 divided by 2, 2.15, we're 2.3 right now. So that's really just 100 kilos. Does that make much of a difference? Not really. We can wait until that fuel goes down to 2.2 roughly, and then we are completely within the limits of what we're supposed to have fuel-wise. All three tanks, remember, this and this is the same tank, or at least feeding the same engine. So all three fuel quantities that are available to each engine are the same now, roughly. So we can end our fuel balancing procedure by turning the fuel pumps in tanks 1 and 3 back on. And when those pumps are on and operating, we turn the transfer valves off. Now we roughly have the same fuel quantity available to each engine. Tank number 1, 4.3 tons available to engine number 1. Tank number 3, 4.3 tons available to engine number 3. And tank number 2, which is this plus this, 4.5 tons available to engine number 2. So the same fuel quantity available to each engine. Easy, isn't it? Alright, and that way we have balanced our fuel, and that is pretty much the only thing that we really need to do for the flight engineer's operation during the cruise. Apart from that, flight engineer doesn't have much to do during the cruise except to monitor and to have fun with the ladies in the back. No, I'm joking. They just care about the captain. The others aren't interesting to the ladies. Sorry, guys. So our airplane is cruising along. We have done the important stuff. We read the Playboy that would have stolen from the gate. So now it's time to prepare our descent and to determine when to descend. Now, there's a couple of ways we can do this. Of course, we do have the top of descent calculator down here in the PMS. That one is useful, 114 miles to run. But that is not exactly accurate. This is based on the bottom of descent altitude that you have entered in the flight setup page down here. If that thing changes, too bad, now you're aft. So how are we going to calculate our actual top of descent? Well, we are going to calculate it the same way that an FMC would in a normal plane, and that is backwards. So let's go ahead and start having a look at our landing airport. That's going to be Barcelona, and we'll be arriving. Let's go ahead and get the weather. Lima, Echo, Bravo, Lima, enter, search. Alright, 210 at 11, 17 degrees, 1019. The moment we get the QNH, we can set that on the Flight Engineers panel. So let's go ahead and set 1019 up here for our cabin pressure for our landing. So, with that set, we know that we're landing on runway 24. So let's start with a look at the airport chart. Far too many charts over here. Here we go. Airport. So, 24 right is the main landing runway, 24 left is the main takeoff runway in this configuration. So we'll be landing on 24 right. Now, let's go ahead and find ourselves the approach chart for runway 24 right. Here it is, ILS Zulu, pin. So that approach starts at Tebla. Okay, fair enough. Unfortunately, we do not have any transition available here, and that is something that you will encounter a lot when you are operating the Tristar with a modern day's world of navigation. So what can we do about this? Well, we can see if there is anything else available that may help. Oftentimes you will still find some transitions with VOR approaches. So let's see, VOR 24 right, do we have something there? Yes we do, look at that. Here's transitions available. Let's pin that chart. So, we have a transition from Sabadell over there, or we have a transition from Calais over here. So let's go ahead and have a look into the star charts to see what we can do. Now, the company has planned us on the Pumal 2 whiskey arrival. Let's go ahead and find that and see if that's any suitable for us. So, Pumal, here's a 2 X-ray, but we don't need that. Pumal 1 Yankee, Pumal 2 whiskey. Here we go. And look at that. That leads us from Pumal to Calais. Perfect. Let's go ahead and use that because we have a transition from there. So we're going to fly the Pumal 2 whiskey arrival to Calais, and from there we are going to fly the transition that we get from the VOR chart to eventually fly the ILS approach. Now, if you do have a transition available on the ILS chart, that is of course even easier, but unfortunately that is often not the time or not the case in the modern day anymore, because nowadays all procedures are based on area navigation, and the INS is not certified for high enough accuracy to navigate with area navigation. So yeah, that's unfortunate, but we gotta live with it. So what are we gonna do now? We are going to have a look at the entire approach charts that we have just pinned. So let's get rid of the Heathrow charts, don't need those anymore. Gonna have a look at those charts backwards and see what we need. So let's start on the ILS that we want to fly. We can see we got Tebla in 2300, but the descent point is a couple miles later, so just remember that. Then we got the chart where the transition is located on. So that's Calais and then Tebla. So this one wants to see Tebla in 2300. Perfect. So Tebla is located, well, what's that? No DME given over here, but that's a couple miles. Let's see, if that's 10 miles, then over here, that's 11, yeah, say 20 miles from outbound Calais. So we got 2,300 foot at Tebla. Do write that down, by the way. Make yourself a little note where you know exactly how far you are and what altitude you want to have at what point. So Tebla 2300, that's what we know now. That means at Tebla we still have a level segment to lose our speed, so let's maintain 250 knots to Tebla. Now that means we don't need to calculate any level segment to lose speed just yet. Now let's go backwards. Got 11 DME outbound Calais, so CLE / minus 11. So that's roughly 10 miles. Using the standard 3-to-1 rule, for every 1,000 feet we use 3 nautical miles. So assuming that this is roughly 9 nautical miles, we add 3,000. So Tebla 2300, so now we're in 5,300 for that waypoint. We know that this is 11 miles, so we can approximate that we're able to lose 4,000 feet here. So let's say that over Charlie Lima Echo, we want to be in roughly 9,000 feet. So now let's have a look at the approach chart. Charlie Lima Echo has to be above flight level 80. We just calculated that we want to be in 90, so we're meeting that restriction and we can plan with level 90. Now let's have a look at the Pumal 2 whiskey arrival. So we got waypoint 465, maximum 250, below flight level 100. So 10 miles from Calais would mean about 3,000 feet. So we said we want to be 9,000 here plus 3,000, so we would be above that. We would be above that altitude restriction. We don't want to be above that altitude restriction, so we set this waypoint as a hard limit. In other words, we write down Bravo Lima 465 at level 100 and 250 knots. So let's go ahead and calculate that further backwards. Our descent speed will be 320 knots, and to reduce 320 to 250, we can approximate 1 nautical mile per 10 knots. We need 7 miles. So 7 miles prior to 465, we want to be in level flight. That means level 100, 7 miles prior to this, 25 minus 7 means we have 18 miles. In 18 miles, again, divide by 3, you get 6,000 feet that you can cover vertically. In other words, at LE, we want to be in flight level 160. Now, we have 16.8 miles between LE and Pumal, and we want to, again, 16 miles. 16 miles equals 6,000 feet. So level 160 at LE plus 6,000 means level 220 over at Pumal. That is exactly in between those. So 220 at Pumal, we can write that down, and that's it. Now maximum 280, we will ask ATC to relieve us of that, but just to have it in mind, if we had 280 here, 250 there, we would have used 3 miles over there. Then we could have been in level 250 at Pumal, would have been easy, but let's just keep our lives easy. So Pumal, flight level 220. Now, of course, we still have to calculate backwards in our flight plan. Let's go down to the OFP. So what do we have? We need the distance between those waypoints. Unfortunately, we only have the remaining distance over here, the distance over here. So Pumal, from Rokan to Pumal, 12 nautical miles. So in 12 miles, 12 divided by 3 is 4. So we know that at Rokan, we want to be in flight level 260. Again, write that down. Then, from Lomra, we got 37 miles plus the 28 over there, inbound to Rokan, and 37 plus 28 is 65. Now, 65 divided by 3 gives us 20,000 feet to cover. We calculated flight level 260, so we've been level 460 now. Obviously, we are not going to be in flight level 460. So, to make our lives easy, there's our top of descent in between those legs. So, prior Rokan. We're in flight level 370. We got a descent to flight level 260 at Rokan. That's 11,000 feet. 11 times 3, 33 miles. So, our top of descent is 33 miles prior to Rokan. Now, looking at our flight plan, we wrote down that Rokan is number 9. So when we're inbound to waypoint 9, we wait until we're 33 miles inbound. And hey, that's it. That's our top of descent. That's as easy as it is. So just a little bit of calculation that you got to run there, but overall not too difficult. Now, let's go ahead and have a look. The Pumal 2 Whiskey arrival tracks inbound to Kaelia, 1535. That's going to be the first waypoint we need for our navigation here, when we return to raw data navigation. So 1535, and that's going to be on a track 146 inbound. So let's select course 1. Here we go, 146 inbound. Alright, so that thing is set up. We are already receiving that VOR as well. Good. Now, after that, we will be flying the approach transition which is also based on Kaelia, outbound, 221, until we intercept the ILS. So we do not need any other nav 8 than Kaelia. What are we going to do? I would tune the airport viewer, 16.7, because that way we have a very easy backup to cross-check our altitude later on in the descent. And look at that, we're actually receiving that thing already. 116 miles from the airport. That's quite useful, isn't it? Now, you will not always have that. That's the reason why we do calculate the vertical track for every single one waypoint, so that we can monitor our vertical profile on the descent into our destination airport. Okay, now that's everything we can set up for the approach. Let's have a look at the ILS. Now that's going to be on a 244 track inbound. We cannot set that yet, since we will need the course 1 to navigate. Okay, that's noted. Now look at that, we're inbound waypoint 9, 27 miles out. That means we can start our descent just now. So let's go ahead and set the altitude down to the nearest level restriction, which is going to be flight level 120. Press vertical speed. And remember, in order to cover 3,000 feet, 1,000 feet per 3 nautical miles, you need a vertical speed that equals 5 times the ground speed. Go down here, ground speed is 530. Let's take 530 times 5, gives us roughly 2,500 feet a minute, a little bit more. Easy. Now in order to monitor our vertical profile on the way down, we can, and determine the exact vertical speeds needed, we can also use a little bit of easy mathematics. So what are we going to do over here? Now, we have the time to the waypoint, 2 minutes. We've calculated the altitude we want to have there, flight level 260. So we're going to get down to level 260 in 2 minutes. That means 5,000 feet a minute. Now, if you're wondering, we started the descent a little bit late. That is the reason why we need to accelerate that descent right now. When we leave our cruising altitude, we set the cabin altitude down to our field elevation. That's basically 0 in Barcelona, so set the cabin down to 0. And with that, our cabin starts descending now. Okay, so we're now flying down. In our profile, we are monitoring our vertical progress by looking at the time over there. And we're heading inbound waypoint number 9, which is Rokan. Supposed to be there at flight level 260. So now we got a minute to run. We are 5,000 feet above the profile, so 5,000 feet a minute, easy going. Something I love about the Tristar is how you can absolutely lower that nose, make it go down, no problem whatsoever. So, one thing you'll notice about the Tristar is that auto thrust does not have a Mach hold mode. So, if you do want to increase your speed, you'll have to increase it in slow steps so that you don't overspeed the aircraft. Now we said we wanted 320 knots on the descent. Let's go ahead and set that straight away, like that. Of course our MMO is already above that at 350. Easy going. Okay, passing Rokan, we are going to join our arrival towards Pumal. And in Pumal we want to be in flight level 220. So that's in 2 minutes. 3,000 feet of cover, so let's go ahead and reduce that rate of descent again. 4,000 feet of cover, 2 minutes, so that's 2,000 feet a minute. Can make that a bit less. 3,000 feet to cover, 2 minutes, so something like 1,700 feet a minute-ish. That way, you got a very precise vertical path down. Now, in my opinion, that is a lot more precise than using the VNAV feature down here, because the VNAV feature doesn't take any constraints or anything into account. If you calculate your position manually, that's much, much easier and much, much more precise. But again, that is different techniques. I would recommend to do it this way. because it just makes your life easier. Okay, we are descending, so let's go ahead and read the descent checklist. That's flight instruments checked, landing data. We haven't done that yet. Let's go down here, landing performance. We can simply calculate the data, which is automatically going to import what we got in our plane, or we do it the realistic way, which is going back here. That's our gross weight, 151.1. So landing weight is probably going to be 151. Enter. Landing elevation is pretty much 0. Barcelona is at field level. The runway is dry and its grid is on. Calculate. Here we go. And then we can also set those speed bugs. Now they're all set automatically for that approach. Makes the life about as easy as it gets. It just changes your target speed as well. So just gotta set that back to wherever you need it. Okay, here we go. So we are approaching Pumal, and from there we can enter the arrival. Here we go. So let's switch this over to radio nav, and you can see we got the Kaelia VOR 1535 up here, and we are pretty much on track. So let's press the VOR button so that we start tracking the VOR for our arrival. You can see we've been slightly off. You can see that up here as well, which was due to a slight drift in the INS. Nothing significant at all. So crossing Pumal, and we've been about in flight level 220. Next up we got Ellie. We have calculated that we want to cross Ellie at flight level 160, so we got to cover 5,000 feet in 2 minutes. That's roughly 2,500 feet a minute, and since we are back in our profile now, doing roughly 500 knots, 2,500 feet a minute, seems pretty much spot on. If you want to do cross-track that you haven't completely messed up, and if you are receiving the airport VOR, you can do it quite easily. That's 60 miles to run, we're in 20,000 feet. 20 times 3, 60 miles, and look at that, 60 miles. So we know that we are spot on with our profile and descending. Now, when we are descending and we are approximately at level 150 or 15 minutes from landing, we are at the ladder right now, then we can turn on the fasten seatbelt and no smoking signs. If you're operating in the United States and you are descending below flight level 180, I would recommend turning on the landing lights at this point, because VFR is allowed up to level 180 and you're flying so fast that every 1 second you can be seen earlier may be saving your life if there is VFR traffic that ATC does not provide separation to. Really, do that. Think about it. You are saving yourself with that. So we wanted to cross Ellie in level 160. We got half a minute to run. We're doing 2,500 feet a minute, so that looks pretty accurate. And after that comes waypoint 465, where we want to be in level 100. We got 7 minutes to get there. That means we need roughly 1,000 feet a minute, but we also need 7 miles to lose our speed, so we are going to descend a little bit faster, let's say at about 2,000 feet a minute. That way we are reaching easy mathematics here again. We need to cover 6,000, we're doing 2,000 feet a minute, that means we need 3 minutes to get there. We are flying 420 knots. Take 420 divided by 60. That gives you roughly 7. So you cover 7 nautical miles a minute. We need 3 minutes to get down there. 7 times 3 is 21. So then you can see we got ample time available to reduce our speed when we get down to the level. Indeed, we got so much time that we can even reduce our vertical speed a little bit in order to make it a bit easier. Now, that is unless you do an error that I just did. I looked at this because in radio mode you're supposed to have your DME up there. Nope, this is your DME. That's a bug. This is showing your INS. That's the distance to the airport right now. Plus a little drift, you can see. Okay, so this is your DME. So let's resume those 2,000 feet a minute. So 10 miles prior to Kaelia. See, 10 miles. We're supposed to be in level 100. We just calculated that we need, now it's about a minute and a half, 7 miles a minute. So we need about 10 miles to get down. Then we're 15 miles prior. That means we have 5 miles to lose our speed to make that 250 knot restriction. Yeah, that sounds about reasonable. I would say we can certainly continue that way. So you can see there are many ways how you can back your vertical navigation up if you do not have any automatics available for that. Really, not much to do there. Not much to do there once you understand what you're doing. Okay, we want to go down to 10,000, please. Like that. Stay in vertical speed mode. So 10 miles until we gotta have reduced our airspeed. We need to cover 2,000 feet, so 7 miles to get down there. Yeah, I think we can start pulling our thrust out. So let's just reduce the target speed to 250 over here. That's a little bit of a gut feeling as well. You will develop that when you are doing this more often. Just aim the stick as closely as possible to the planned crossing altitudes. So there's 1,000 to go. Let's reduce our vertical speed, 1,000 feet a minute. Speed is coming back nicely. And by the time we are at 10 DME, 10 DME up there, by the time we're at 10 DME, we are supposed to be at 250 and 10,000. But definitely making the altitude and the speed, so that's easy going. Now remember from the flight plan, we aim to cross Charlie Lima Echo at 9,000. So passing 10 right now. The airplane goes into altitude capture mode. Speed is already down, so let's go down to 9,000 up next. Vertical speed. We're now doing a ground speed of 300 knots, which means we cover 5 nautical miles per minute. 300 divided by 6. 60. Well, 60 knots is 1 mile per minute. And therefore, we have 2 minutes to get down to 9,000, so let's do 500 feet a minute. Alright, passing through 10,000, the landing lights and the taxi and turn-off lights are coming on. Now you can keep the taxi and turn-off lights off if you want to use them as a reminder for your landing clearance. But the landing lights need to be on, the seatbelts need to be on. On the fuel panel, make sure that the tank 1A transfer and tank 3A transfer switches are off. Make sure that all the fuel tank pumps down here are on and that all the transfer feed valves are closed. Okay. So, let's take a moment to talk about when to initiate a turn over a VOR. So, we're approaching Kaelia, and we need to turn onto a 221 track outbound. Let's go ahead and pre-select 221 on the heading. And we can see that we need to turn by around about 90 degrees. Now, if you do standard grade 1 turn, you need 2 minutes for 360. That means we need 30 seconds for this. We cover 5 miles a minute, so half a minute we are going to cover 2.5 miles. On top of that, we also have the slant range error. 6,000 feet equals 1 nautical mile. So basically, at 3 miles, we want to start the turn. Here we go, 3 miles. Let's start the turn. We're going to select the course towards 221. Let's see how that's going to work out. Also, we do want to continue the descent all the way down to 2300 here now. So, vertical speed, and again, 300 times 5 is 1500 feet a minute for our standard descent. Let's see how well that's going to work out. Now at this point we are descending below the transition level. QNH is 1019 as we had set up there previously. So let's go ahead and set that QNH. Here we go, 1019 is set cross-check, passing 8.5 now. So we're almost over the station. We are just passing the target radial, so that looks quite good. Let's go ahead and re-intercept that using the heading mode. So there is a very slight overshoot, but look at that. Pretty much spot on. 2 to 1. Looking excellent. Okay, then let's go ahead and read the approach checklist. And VOR mode on so that we keep tracking this. So approach checklist. Fasten seatbelts are on. Exterior lights on. Altimeters. QNH 1019 is checked. Flaps and slats reading up. Radio and nav switch is on radio. No smoking sign is on, and the fuel panel is set. Alright, and that's the approach checklist completed. Now that we are closing in on the field, we can also use the airport VOR for a bit of vertical management over here. We're in the 7000, 7 times 321. We got 23 miles. So we are a little bit below the 3-degree path, but we also still need to lose a bit of speed. In other words, our profile is pretty much spot on. Now, the next waypoint we have on the flight plan that we wrote down in the approach preparation is to cross the 11 DME point outbound in 5,300. We're at roughly 10, so we're going to lose 300, so we'll be in 5,700. Tiny bit high right now. Let's go ahead and help it. Now, since we are correctly established on the radial, let's go ahead and tune our ILS. I'm going to switch over in heading mode over here. Now we can go to the ILS chart. Got 244 inbound, 109.5. So let's tune 109.5 and 244 degrees. That's set. So now we're basically tracking the VOR radial outbound using heading mode, and we're basically going to fly and follow this heading all the way until we are intercepting the localizer. Now you could use VOR2 to back up the outbound radial, but since we've been stable on the radial, I'm rather using heading mode to track this, so that I can set Barcelona VOR 116.7 on here, keep it over there, and select the 241 radial outbound, which we are going to fly in case I missed approach. So that way we got our active ILS and we got our missed approach pre-selected. The reason I'm pre-selecting this, if we go around, I'm still going to tune it here and here, but that way we got a stable indication already, and we don't need to go to the charts and look up like, oh, what do I maybe want to use or not. Okay, so we're at 14 miles. The localizer should come active any moment. Let's go ahead and arm the localizer mode, which should theoretically arm already. Probably only gonna do that once the actual localizer starts coming in. So we're reaching 2300. Let's start reducing our airspeed. We're gonna go down right to 205 knots. Checked. So localizer mode still isn't doing it. Might have to get a bit closer and wait until the localizer actually starts coming in. 12 miles out now, so that's a good moment in time to start slowing down. Here we go, localizer alive. Still not doing it. Interesting. Okay, well, in that case, we are going to disconnect the autopilot. Must be a little system bug there. Disconnect the autopilot and intercept that localizer manually. So, reaching the first bug, we are going to select the flaps into 4. And then we can start reducing our speed to 185. And reaching the second bug, we are going to go flaps 10. Alright. At this point in time, let's go ahead and select the auto brake. Normally we only do that once the gear is down, but auto brake coming down, the glide slope is alive. So let's switch auto thrust off and take that stuff over manually. Supposed to be in 2300 feet over here. And at the speed bug here in the middle. Now, we're intercepting the glide slope here. Thrust idle, set missed approach altitude. And that missed approach altitude is 3000. So, going through 60 ME on the final, or 2200 on the radio altimeter, we are going to get the landing gear warning horn when the engines are in idle. So, that is a good point to extend the landing gear. 6 miles, usually completely fine. And then we go to flaps 22. And flaps 22 is basically the inner speed bug that we have down here. Now from there on, we are going to reduce down to landing speed, which is basically VREF plus wind additive. So we approach 153 down there. And that's basically down here. Alright, and at that time, flaps 33. And with that, let's quickly pause the simulation here and talk about a couple things. So, first of all, let's talk about the approach criteria over here. So, stabilized approach criteria. What exactly do we need and at what time do we need it? Lockheed says since the airplane is a little... Let's say since the airplane is a little heavy and has quite the inertia, we are always using the 1000 foot gate. So at 1000 feet above the landing field elevation, we want to be completely stabilized. What does that mean? Well, want to be on pitch, on glide slope, on localizer, with it, everything means within 1 dot, on speed, so no lower than VREF, no faster than V approach plus 15, and basically between those two. We have to have an appropriate rate of descent, an appropriate thrust setting, the landing gear has to be down, and the flaps have to be in the landing setting. You do not have to arm the speed brake in this aircraft, just saying. That's basically happening automatically. Now, let's talk about one of the specialties of the L1011. The L1011 is equipped with a so-called direct lift control feature. You don't have to actively think about that feature while you're flying, but you should be aware that it exists, because the 1011 may handle a little strange on approaches. Now, what direct lift control does is that with the flaps and landing configuration, the airplane will use or will extend the spoilers to a certain setting. Now, that means that you get a certain pitch attitude on final. When you are pulling your control column towards you, in other words, if you would in an ordinary airplane, raise the nose. What the 1011 does is to instead lower the spoilers, therefore increasing your lift and reducing your rate of descent. When you push forward, the spoilers are simply going to extend a little bit further, lowering your lift and increasing your rate of descent. Therefore, you will have a much more constant pitch attitude than you would on your typical aircraft, and instead you are going to get your variations in the rate of descent through the variation in the spoilers. That's quite a cool thing. That is really quite a cool thing. Now, you do see that on modern aircraft like the 777 Freighter or the 737 MAX as well, but Lockheed were the first to do this. Now, that's the basics. Now, maintain good control of your airspeed. You really want that speed to be spot on. Otherwise, if the speed varies greatly, then you are going to get great pitch variations. Auto thrust is not very accurate here, at least not the way iniBuilds modeled it. I'm not sure if it would be on the real airplane. So auto thrust is not very accurate. I do recommend using manual thrust for landing the 1011. Now, with all of that done, we're established on final approach. It's time to read the landing checklist. And the landing checklist is rather long, so if you don't have the capacity to do that while you're flying manually, don't fuck your approach up the two most important points on the landing checklist: gear down, flaps down. Anything else is supplementary. But let's go over what the landing checklist actually includes. So we got QNH 1019 is set. That's important because of the minimum. Remember, you only have a radio altimeter minimum in here. So if you want to read out the correct callouts from the barometric altimeter, then the correct QNH needs to be set. Okay, so QNH set, landing gear down, continuous ignition as required. Now, do turn it on when you got heavy precipitation or when there is snow or slush expected on the runway. Cabin crew alerted, hydraulic panel checked. Again, that's just checking for any malfunctions which could become relevant for the landing gear. Brake system and anti-skid checked. So brake system down here, looking good. Anti-skid is showing on. Flaps 33 degrees. Down here, all set. And DLC alpha checked. That's the direct lift control. Alright, and that's the landing checklist complete. So, let's go ahead and continue that approach. And then while we are flying the rest of the approach, we will also talk a little bit about the touchdown itself. So let's go ahead and by the way, close that GSX panel, that's annoying, and go out of the pause. So, thrust in order to maintain the speed at the speed bug. Trim the airplane out. And make sure that you're exactly stabilized. You will notice that the pitch doesn't always react the way that you would expect based on your control column input. That's due to the direct lift control feature in action. Now, aim to get really a stable pitch attitude here and a stable rate of descent following that glide slope. When everything is stable, the 1011 is a really stable platform, flies really nicely. You do not have radio altimeter callouts, so you will have to get used to the attitude on final and when to start the flare. It took me 2 or 3 landings to get that right, so just try to get that right. Now, the flare should be initiated latest by 30 feet on the approach. Unfortunately, since you don't have radio altimeter callouts, you kind of can try to read it from down here from your radar, but at that time you should be looking outside the window. Basically, at 50 feet, look out the window. At 30 feet, initiate the flare, and then smoothly retard the thrust levers so that your engines reach idle by the time you touch down. Be careful with the nose, as the nose wheel has a tendency to just fall down. Prevent it from doing that. Rather, land the nose wheel actively. Right now, look at how I'm using a yoke, but the pitch is barely responding, as the DLC is doing everything with the spoilers. Below 200 feet, we don't really want to follow the puppy or the glide anymore. Maintain a stable rate. Here's 30, flare, idle, and actively fly the plane down. Like this. Touchdown. Extend the spoilers, extend the reversers, maintain the center line. If the auto brake is not operating, then do apply brakes manually. But here we go, past 100, past 80, reverses back in idle, manual brakes, and then we're going to vacate the runway on the next available and useful exit. And with that, welcome to Barcelona. Alright, vacate the runway completely, aka get your entire airplane behind the line. And only when the entire airplane is behind the whole throttle line, only then stop the aircraft to do the after landing procedures. You can see I'm really driving it completely onto the taxiway here. I'm even aligning it with the taxiway, just be sure that you have ATC clearance. In the real world they're good, in Flight Simulator not always. Alright, and now that we're completely clear of the runway, in the real world you would keep the airplane taxiing while you do the after landing items. In the simulator, for simplification, we are just going to set the park and brake over here. And with that, we are getting to the after landing items. So, first of all, congratulations, you made it, you're on the ground. and the airplane is still in one piece and can even be used again. With that, we have fulfilled the most important parts of our mission. But we are not completely done yet. Let's go ahead and start working the after landing items. So the iniskid is going to go off. That means we are actually going to unlap the switch as well. Auto brake off, landing lights off, strobe light off, continuous ignition off, air data and sensor heat off, windshield heat panel, captain and first officer should be showing idle right now, and the side windows should be switched off. Then we're moving down. Stabilizer trim is going all the way to 0. Then the speed brake lever is going up. The flap lever is going up. Transponder into alt off and weather radar off. Now that's everything we had to do in the front over here. Let's go back to the flight engineer's panel. The flight engineer is going to start the APU, so master power switch on, then starter until the door and transit light goes out, which is... oh, come on. Now? Okay, and then we go down to the fuel panel, open all the transfer valves, and we are going to ensure that only one fuel tank pump is on. So all of those going off. Again, that's in preparation for the APU, which is rather weak on the electrical generator there, so we only want to run a single fuel pump, and the 1 alpha and 3 alpha transfer pump switches are off and unlatched. Okay, and that's the after landing items complete. Let's now go ahead and read the after landing checklist, which is quite the long one as well. So that's anti-ice off, windshield heat, idle, air data sensors off, continuous ignition off, iniskid off, landing lights and strobes off, speed brake lever forward, flaps and slats up and retracted, trim 0, 0 and 0. Then radar and transponder set and off. That leads us to the flight engineer. So that's going to be the electrical panel, where we can turn the galley powers off at this point as well. So electrical panel checked, fuel panel, again, one pump with the cross feeds. Checked, ECS panel. Over here, once the APU is available, you could already turn the APU bleed on, but then you'd have to turn the engine bleeds off. Can do that, don't have to. So that's why it just says checked in the checklist. APU on, and brake system down here is checked, and that's the after landing checklist complete. Alright, so with that done, let's go ahead and release that parking brake. Remember, you're at a very light weight now, so the aircraft is definitely going to roll in idle. So let's just go ahead and find ourselves a gate and get parked. Now, any of those procedures from the flight engineer can be automated using the automatic flight engineer in the menu, autocomplete. Over here, you can have him do everything. That way, you really just have to focus on the actual job of the captain. That makes flying the 1011 incredibly easy, even easier than flying most conventional, or not conventional, but most modern computer-driven aircraft. Alright then, let's go right in here and find ourselves a gate. Remember the taxi speeds, 30 knots straight, 15 knots on an apron, 10 knots for a turn, and absolutely do remember to apply sufficient oversteering so that the main wheels stay on the taxiway centerline. Very important here, guys. Alright, this is looking pretty good. And then I'm just going to go to the right over here and then next left, taking the next parking stand there. Alright, entering the gate, turn off the taxi and the turn-off lights and ensure that the weather radar is off, so no mode indication down there. And then with sufficient oversteering so that you do not use up the entire space in the gate while turning in, but only use minimum space, turn yourself into the gate. Again, the easiest way is to imagine in your head where the main landing gear is located and then keep the center line in between the main landing gears, which is the point that the airplane is turning around. Okay, If the guidance system is not working, then you just have to help yourself. This one is working. Very nice. So let's go ahead and park according to the guidance system. And that looks good. Stop. Okay, we're going to stop the aircraft. We are going to set the park and brake. And before we can shut the engines down, there's a little work to do for the flight engineer. So let's go over to his panel and start over there. So if APU power will be used, ensure that the generator field breaker is closed and the generator breaker is closed. Then we are going to ensure that the APU actually delivers power, or the external power if you are using the external power directly. Alright, with that done, we can start shutting down. So fuel switches, all three going off, anti-collision light is going off, seatbelt sign is going off. Then we can do a little accuracy check on the INS that I'm going to talk about in a moment, and the transponder mode is going off. On the flight engineers panel, we are going to switch off the ATMs. As long as the APU is running, we ensure that one tank pump is on, and we can already close the crossfeed valves, and then we are going to open the APU bleed air shutoff valve. Ensure that the airplane is configured for APU operations. Use the packs as necessary. You can use all three if it's especially hot. Otherwise, a single pack is sufficient for this. Alright, and then let's go ahead and read the shutdown checklist. That's engine rundown normal, park and brake on, MSUs, so IRNS mode select units, are still on nav at this point. The exterior lights are set, standby power remains armed for the next flight. So fast mode's off, max indicators, that's on the engine panels down here. Quick check that we haven't exceeded any limits, so the red line for N1 is about at 100, for the TGT is well below the red line, for the N3 is at 100. Alright, that's looking good, max indicators reset. Then, on the flight engineers panel, the ATMs are off. Hydraulic panel is checked, battery switch remains on, fuel panel 1 on, and ECS panel is set, which mainly means that the APU is pressurizing the, or feeding one of the packs to provide temperature control. And that's the shutdown checklist complete. Well, my friends, with that, welcome to Barcelona. There's a couple of things that we can do to verify that our aircraft has operated correctly. So down here we have our position. Let's go down and enter that as a waypoint. Doesn't matter which waypoint it is now. We're on number 3 right now. Well, let's just scroll to, I don't know, number 6. Alright, so we're at north 41.17.5. And east 2044. Like that. Now that's waypoint number 6. If we go ahead and enter direct from present position to waypoint 6, and now go to the distance and time, unfortunately there is a little bug that is immediately transiting from waypoint 6 to waypoint 7. Now, it should stay on waypoint 6 really. If it did that, it would tell you the distance up here. That's what the thing that's currently showing 160. Again, that's the waypoint 7, so should be the waypoint 6. Unfortunately, is currently bugged as it's automatically transiting. But that distance that you see over here would be the drift of the INS unit. You verify that for all 3 units, and then you ensure that that number hasn't become excessive. Now, what excessive means really varies depending on the length of the flight. It's mostly, for a 10-hour flight, you're looking at about 20 miles. For a 5-hour flight, 10 miles. For a 2-hour flight, 2 miles-ish. And those are the limits for INS operation. That also gives you an idea how well your system is working or not working. And you would do that after each flight before turning the INSs off, because once they're turned off, obviously they lose the alignment and you lose that type of information. Alright, now we have done that, or at least we assume that we've done that within the scope of what the iniBuilds currently allows us. So right now it's time to start with the secure procedure. Now, the secure procedure is pretty easy. And we are going to do that again right from the iniBuilds manual. So we start with the emergency exit lights, which are off, standby power off, master radio switches off, INS is off. And that's everything we need to do from the captain's seat. Now let's go to the flight engineer's seat. Over here, the galley power is off. If the APU has been used, which it has, we're gonna trip the generator breaker, turn the APU bleed valve closed. Then we are going to turn off the shut-off valve, hit the APU stop button, and here we go, APU is shutting down. Now, we need to wait 2 minutes before we can turn the master power switch off. In the meantime, fuel tank pumps unlatch the last switch that you have been using. And now we just got to wait until the APU shutdown is complete. Once it is, turn off the battery switch, and that's it. Then we got the secure checklist, which is window heat off. So up here and up here. Window heat is off, radar is off, crew oxygen is off, and all the internal lights are, well, supposed to dim them. Whether or not you want to do that, up to you. And that's the securing aircraft checklist complete. So the APU is off, APU master power off, battery off, and that's it. With that, welcome to Barcelona, everyone. I do hope that you enjoyed this tutorial. Leave your feedback in the comments underneath the video. As always, like, comment, and subscribe. Let me know if you've got any questions left at any point, and put them into the comments underneath the video. Again, do let me know your feedback if you liked me providing this as a single all-in-one tutorial, or if you would have preferred several different videos. Up to you. Let me know in the comments below, then I can adjust for future aircraft tutorials. Thank you very much for watching. As always, like, comment, and subscribe. And with that, I'm really looking forward to seeing you all again on the next one.